For much of modern astronomy, the expansion of the universe appeared to be a settled matter. Observations showed that galaxies are receding from one another, and the farther away a galaxy lies, the faster it appears to move. This behavior was interpreted as evidence that space itself is expanding, carrying galaxies along with it. For decades, this picture fit comfortably within observational uncertainty. That situation has changed dramatically. As measurements have become more precise, the expansion of the universe has begun to reveal inconsistencies that cannot be explained by experimental error alone. What once looked like a simple cosmic trend has become one of the most pressing problems in contemporary cosmology. If you're intrigued by the possibility that something fundamental is broken in our understanding of the cosmos, subscribe now. The mystery of why the universe's expansion refuses to behave as expected is only beginning to unfold, and uncovering what went wrong may reshape everything we think we know about the universe. The expansion rate of the universe is quantified by a parameter known as the Hubble constant, which links the distance to a galaxy with the speed at which it is receding. In a universe governed by a single, consistent expansion history, this value should be the same regardless of how or where it is measured. Instead, modern observations have split into two distinct camps that produce conflicting results. Measurements based on the nearby universe consistently indicate a faster expansion rate than those inferred from conditions in the early universe. The difference is not small. It is large enough that it challenges the internal consistency of the standard cosmological model and forces astronomers to re-examine assumptions that were once considered secure. Local measurements of expansion rely on observing galaxies close enough that their distances can be determined directly or through well-calibrated astronomical objects. These observations typically produce values of the Hubble constant in the range of roughly 72 to 74 kilometers per second per megaparsec. In contrast, measurements derived from the early universe, particularly those based on the cosmic microwave background, yield values closer to 67 or 68 kilometers per second per megaparsec. The discrepancy of about 5 to 7 kilometers per second per megaparsec corresponds to a difference of approximately 9%. Given that modern measurement uncertainties are often below 2%, this disagreement has reached a level that cannot be ignored by statistical standards. The early universe measurements come from observations of the cosmic microwave background, the faint afterglow of radiation, released when the universe was about 380,000 years old. This radiation fills the entire sky and has a nearly uniform temperature of about 2.7 Kelvin, with tiny fluctuations at the level of 1 part in 100,000. These fluctuations encode information about the density of matter, the geometry of space, and the expansion rate at that early time. By analyzing their angular scale and distribution, cosmologists can infer how fast the universe was expanding and then extrapolate that expansion forward to the present day. The most precise measurements of this radiation were made by the Planck satellite, which mapped the sky with unprecedented resolution before concluding operations in 2013 and releasing its final data in 2018. The Planck results are internally consistent and align closely with predictions from the standard cosmological framework. They also agree with earlier measurements made by the Wilkinson microwave anisotropy probe, though with far smaller uncertainties. When analyzed within the lambda cold dark matter model, the Planck data tightly constrain the expansion rate, leaving very little room for adjustment without altering other parameters. This tight coupling between different cosmological quantities is one reason the expansion discrepancy is so difficult to resolve by simple modifications. The tension arises when those early universe predictions are compared to direct measurements of the present-day universe. Observations made using the Hubble Space Telescope, along with large ground-based observatories in Chile and Hawaii, measure distances to nearby galaxies using astrophysical objects whose intrinsic brightness is well understood. These measurements do not depend on assumptions about conditions shortly after the Big Bang. Instead, they are anchored in stellar physics, nuclear reactions, and well-tested models of stellar evolution. The fact that these two fundamentally different approaches yield incompatible expansion rates suggests that the problem is not a simple observational mistake or a single flawed dataset. The modern cosmological model, known as lambda cold dark matter, provides the framework in which most of these measurements are interpreted. It assumes that the universe is dominated by dark energy, which drives accelerated expansion, and cold dark matter, which shapes the growth of cosmic structure. Ordinary matter makes up only about 5% of the total energy content of the universe, while dark matter accounts for roughly 27% and dark energy for about 68%. These proportions have been inferred from multiple independent observations, including galaxy rotation curves, gravitational lensing, and the cosmic microwave background. Within this framework, the expansion history of the universe is tightly constrained across cosmic time. The first hints that something might be wrong emerged more than a decade ago. As observational techniques improved and sample sizes increased, local measurements began to drift slightly higher than early universe predictions. Initially, the discrepancy was small enough to be attributed to calibration errors, dust effects, or unrecognized biases in galaxy selection. As more data accumulated and those potential issues were corrected, the difference persisted. By the time Planck delivered its final results, the disagreement had grown sharper rather than diminishing. Instead of converging on a single value, the two approaches were pulling further apart. What makes the situation especially compelling is the consistency within each category of measurement. Local measurements using different telescopes, different observing strategies, and different calibration methods all point toward a similar higher expansion rate. Observations from the Hubble Space Telescope, the Very Large Telescope, and other facilities converge within narrow margins. Early universe measurements, including those derived from the cosmic microwave background and from large-scale galaxy surveys, independently converge on the lower value. This internal agreement makes it increasingly unlikely that a single overlooked error is responsible for the entire discrepancy. The expansion anomaly also affects related cosmological quantities. The age of the universe, for example, depends directly on the expansion rate. A faster expansion implies a younger universe, while a slower expansion implies an older one. Using early universe measurements, the age of the universe is estimated to be about 13.8 billion years. Local measurements suggest an age that is several 100 million years younger, while both values remain broadly consistent with the ages of the oldest globular clusters and metal poor stars. The difference is large enough to affect detailed comparisons between stellar evolution models and cosmological timelines. Beyond age estimates, the expansion rate influences how structures such as galaxies and galaxy clusters form and evolve. A mismatch in expansion history affects predictions for how quickly matter collapses under gravity and how density fluctuations grow over time. Observations of galaxy clustering and weak gravitational lensing show mild but persistent tensions with predictions based on early universe data. These discrepancies are smaller than the Hubble tension itself, but they point in a similar direction, reinforcing the sense that the expansion problem may not be isolated. The scientific community has responded by subjecting both local and early universe measurements to intense scrutiny. Calibration procedures have been re-examined repeatedly, detector sensitivities recalibrated, and data reduction pipelines independently reconstructed. New observational programs have been designed specifically to test for hidden sources of error, including those related to interstellar dust, metallicity effects, and environmental biases. So far, none of these efforts have identified a correction large enough to reconcile the conflicting expansion rates. As measurement uncertainties have decreased, inconsistencies in the inferred expansion rate have become more apparent. Investigating the origin of this discrepancy involves examining how distances are measured in the nearby universe, how those measurements are anchored to physical objects, and how confidence is established at each step. This includes the methods used to translate observed brightness and motion into quantitative cosmic distances, where early indications of the expansion discrepancy were identified: redshift, distance, and the first signs of trouble. To understand why measurements of cosmic expansion began to diverge, it is necessary to examine how astronomers determine that the universe is expanding in the first place. The foundational observational signal behind expansion is redshift, a measurable change in the wavelength of light emitted by distant objects. When light from a galaxy is stretched toward longer wavelengths, it indicates that the space between the source and the observer has expanded during the light's journey. Redshift is not an abstract concept. It is directly observed in the displacement of spectral lines produced by known atomic transitions. These lines act as precise fingerprints, allowing astronomers to measure recession with extraordinary accuracy. Early observations of redshift, first systematically catalogued by Vesto Slipher in the 1910s, already hinted at a universe in motion, though the tools of the time lacked the precision to reveal the subtleties that would emerge a century later. The challenge is that redshift alone does not reveal how fast the universe is expanding unless it can be paired with an independent measure of distance. Recession speed is inferred from redshift, but distance must be measured separately using astrophysical indicators whose intrinsic properties are known. The relationship between distance and redshift is what allows astronomers to construct an expansion rate. In the early decades of observational cosmology, large uncertainties in distance measurements limited detection of small differences in expansion rates. Redshift measurements are among the most precise data in astronomy. Modern spectrographs can measure wavelength shifts to better than 1 part in 100,000. Instruments such as the high-resolution Echelle spectrometer at the Keck Observatory in Hawaii and the ultraviolet and visual Echelle spectrograph at the Very Large Telescope in Chile routinely achieve velocity precision of a few kilometers per second, even for galaxies hundreds of millions of light-years away. Large spectroscopic surveys, such as the Sloan Digital Sky Survey, have catalogued redshifts for over 4 million galaxies, creating a robust statistical foundation for cosmological studies. This level of precision means that redshift itself is not the weak link in measuring cosmic expansion. The difficulty lies in translating those measurements into accurate cosmic distances, which remain surprisingly challenging. Distance measurement in astronomy is fundamentally indirect. Unlike terrestrial measurements, there is no single ruler that can be extended across intergalactic space. Instead, astronomers rely on a sequence of overlapping methods, each calibrated against the previous one. This sequence is often referred to as the distance ladder, though the ladder metaphor hides the complexity and potential pitfalls involved. Each rung relies on specific astrophysical assumptions, environmental corrections, and statistical treatments that become increasingly important as precision improves. The ladder begins with the closest stars, extends to variable stars in nearby galaxies, and ultimately reaches distant supernovae in galaxies billions of light-years away. The first rung involves geometric techniques, parallax measurements, which track the apparent shift of nearby stars as Earth orbits the Sun, provide direct distances within the Milky Way. Historically, parallax was limited to stars within a few hundred light-years. The European Space Agency's Gaia mission, launched in 2013, revolutionized this step by measuring parallaxes for more than 1 billion stars with a precision of a few micro-arcseconds. For stars within a few thousand light-years, distance precision can now be better than 1%. These measurements anchor the entire distance framework, ensuring that subsequent rungs of the ladder are tied to a solid baseline. Beyond the range of parallax, astronomers rely on astrophysical objects with predictable luminosities. Certain types of stars vary in brightness in regular, well-understood ways that are directly linked to their intrinsic power output. Cepheid variable stars, first studied systematically by Henrietta Leavitt in the early 20th century, are a prime example. Their pulsation period is tightly correlated with intrinsic luminosity, allowing astronomers to infer distances by comparing observed brightness with predicted luminosity. Other distance indicators include RR Lyrae stars, tip of the red giant branch stars, and surface brightness fluctuations in elliptical galaxies. These methods extend measurements into nearby galaxies and allow the distance-redshift relationship to be mapped across the local universe. Increasingly precise distance measurements were combined with highly accurate redshift data. In the late 1990s and early 2000s, surveys of galaxies within roughly 100 megaparsecs revealed a tight relationship between redshift and distance, known as the local Hubble flow. As datasets expanded and calibration improved, some galaxies at similar distances implied slightly different expansion rates depending on which distance indicators were used. These differences were small at first. Initially, these discrepancies were attributed to peculiar velocities. Galaxies do not simply follow the smooth expansion of space, they also move under the influence of local gravitational fields. Clusters, filaments, and superclusters induce additional motions that can distort the redshift-distance relationship, especially at smaller scales. For instance, galaxies within the Virgo cluster exhibit velocities up to several hundred kilometers per second relative to the average Hubble flow, enough to temporarily obscure the underlying expansion rate. Astronomers developed increasingly sophisticated models to correct for these effects, incorporating data from large-scale surveys such as the 2-micron All-Sky Survey and the Sloan Digital Sky Survey. While these corrections reduced scatter, they did not eliminate the emerging pattern of slight overestimation in local expansion measurements. As observations pushed farther out, beyond scales dominated by local gravitational effects, the discrepancies persisted. Beyond roughly 100 to 200 megaparsecs, statistical models predict that peculiar velocities should average out, allowing redshift-based expansion rates to stabilize. Yet different galaxy samples continue to indicate slightly higher expansion rates than those inferred from early universe data. Measurements from large galaxy surveys, including SDSS and 6DF, confirmed this persistent deviation across multiple observational programs. Redshift surveys themselves became increasingly comprehensive and ambitious. Projects such as the 6DF Galaxy Survey, the Baryon Oscillation Spectroscopic Survey, and the Dark Energy Spectroscopic Instrument mapped hundreds of thousands to millions of galaxies across vast volumes of space. These surveys confirmed that redshift measurements were consistent across instruments, observing teams, and data reduction pipeline. Differences in expansion rates were therefore associated with distance measurements rather than redshift measurements. Distance indicators, however, were undergoing continuous refinement. Improved photometric calibration, better characterization of stellar populations, and corrections for interstellar dust and metallicity effects all contributed to tighter and more reliable distance estimates. Space-based observations, particularly from the Hubble Space Telescope and later the James Webb Space Telescope, reduced atmospheric interference and provided more stable and consistent measurements of Cepheids and supernovae. As these improvements accumulated, the uncertainty in local expansion measurements decreased, revealing a systematic difference from early universe values. By the mid-2000s, astronomers observed that distances inferred using certain stellar indicators consistently implied higher expansion rates than those extrapolated from early universe observations. The effect persisted across multiple samples, instruments, and independent research groups, indicating that measurement inconsistencies were not due to individual datasets. Another complication came from statistical treatment of distance data. When small systematic offsets exist, averaging large datasets can amplify their impact rather than suppress it. Researchers reanalyzed archival data, applying uniform calibration standards and updated corrections for metallicity, dust extinction, and stellar age. While individual distances shifted slightly, measurements using local indicators remained systematically higher than those extrapolated from early universe data. Importantly, redshift measurements themselves showed no comparable drift over time. The same galaxies observed years apart with different instruments produced consistent recession velocities. This stability reinforced confidence in the velocity side of the expansion relationship. The discrepancy therefore originates from differences in how distances are measured and calibrated. Redshift-based velocities and independently inferred distances showed an increasing discrepancy. Researchers investigated whether environmental factors such as stellar population age, metallicity gradients, or local interstellar extinction might systematically bias distance indicators. These factors were real and measurable, but modeling showed they could not account for the full discrepancy. By the early 2010s, precise redshift surveys and highly calibrated distance measurements confirmed that local expansion rates consistently differed from those inferred from early universe observations. The difference became more pronounced as instruments, surveys, and analysis techniques improved. Investigating the discrepancy requires detailed examination of the specific objects used to construct the distance framework, including variable stars and supernovae that provide key calibration data. The Hubble constant, a number under siege. At the heart of the cosmic expansion puzzle lies a deceptively simple number, the Hubble constant. Denoted as h0, it represents the rate at which the universe stretches per unit distance, expressed in kilometers per second per megaparsec. Conceptually, the Hubble constant links recession velocity to distance. A galaxy 1 megaparsec away should appear to recede at h0 kilometers per second. This number is foundational because, in a homogeneous universe, it should be consistent regardless of where or how it is measured. Yet, recent decades have revealed that its measured value depends crucially on the method and scale, transforming a previously straightforward parameter into a source of significant tension in cosmology. The pursuit of H0 began with Edwin Hubble's seminal work in the 1920s. Using the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble measured distances to nearby galaxies and correlated them with redshift data from Vesto Slipher. His initial estimate for the expansion rate was approximately 500 kilometers per second per megaparsec, dramatically higher than modern values. This discrepancy was later traced to overestimated galaxy luminosities, misclassified Cepheid variable stars, and limited resolution of photographic plates. Walter Bade's work in the 1940s, distinguishing between population 1 and population 2 stars, effectively doubled the distance scale for nearby galaxies, reducing H0 estimates to roughly 250 km per second per megaparsec. Subsequent improvements by Alan Sandage and Gustav Tammann throughout the 1950s and 1960s brought values down further to the range of 5,100 km per second per megaparsec, though the debate remained highly contentious, reflecting the challenges inherent in measuring cosmic distances accurately. By the late 20th century, the development of space-based telescopes revolutionized H0 measurements. The Hubble Space Telescope, HST, launched in 1990, enabled precise photometry of Cepheid variables in nearby galaxies. The key project on the Hubble constant, conducted by Wendy Friedman, Robert Kennicott, Jeremy Mould, and collaborators, measured over 800 Cepheids in 31 galaxies, calibrating distances with unprecedented accuracy. They reported a value of 72 kilometers per second per megaparsec, with an uncertainty of 10%. Their methodology incorporated corrections for metallicity, dust extinction, and crowding effects, setting a new benchmark for cosmology. This effort was complemented by ground-based observations from observatories such as the Cerro Tololo Inter-American Observatory, which monitored Cepheids in the Large Magellanic Cloud and other nearby galaxies to refine the baseline calibration. Technological advancements continued to enhance measurement precision. The replacement of photographic plates with charge-coupled devices, or CCDs, dramatically increased sensitivity and linearity of light measurements. Advanced photometric pipelines allowed for accurate background subtraction, and modern statistical techniques enabled simultaneous fitting of multiple distance indicators, including Cepheids, RR Lyrae stars, and the tip of the red giant branch method. By the early 2000s, a growing number of independent teams, using different calibrators and distance indicators, began reporting H0 values converging between 67 and 74 kilometers per second per megaparsec. Despite overlapping uncertainties, the persistence of differences hinted at a subtle, systematic discrepancy that would later grow into a significant challenge. A major turning point in the debate came with the advent of early universe measurements. Instead of directly observing galaxies and their velocities, these methods rely on the cosmic microwave background, the relic radiation from the Big Bang. Observatories such as the Wilkinson Microwave Anisotropy Probe and later Planck mapped temperature fluctuations in the CMB with exquisite precision. By analyzing the angular scale of the acoustic peaks imprinted on the primordial plasma, cosmologists infer the Hubble constant indirectly, assuming the standard LCDM cosmological model. These methods yielded H0 values around 67 kilometers per second per megaparsec, systematically lower than local measurements. The difference of roughly 5-6 kilometers per second per megaparsec, though small numerically, corresponds to a nearly 10% discrepancy in expansion rate and exceeds 4 standard deviations in statistical significance. Local H0 measurements continued to improve alongside early universe estimates. The SH0ES, or supernova H0, for the Equation of State project, led by Adam Rees, expanded the Cepheid calibration sample to over 1,200 stars in more than 70 galaxies, linking them to Type Ia supernova distances. This massive dataset yielded a Hubble constant of 73.04 kilometers per second per megaparsec with a 1% uncertainty, illustrating how systematic refinements such as better characterization of Cepheid metallicity, color corrections, and improved photometric calibration reduced error margins. Maser-based distance measurements provided additional confirmation. Water megamasers in the accretion disk of NGC 4258 orbit the galaxy's central black hole at measurable velocities, allowing geometric distances to be derived with 2-3% accuracy. These results are consistent with local H0 values derived from Cepheids and supernovae, reinforcing the robustness of high local expansion rates. Modern measurements have achieved substantially reduced statistical uncertainties. The 2018 Planck results constrained H0 to 67.4 plus or minus 0.5 kilometers per second per megaparsec, while the SH0ES project reported 73.04 plus or minus 1 kilometers per second per megaparsec, corresponding to a discrepancy exceeding 4 sigma. In observational cosmology, disagreements of this magnitude have historically been associated with identifiable systematic uncertainties. Current analyses show that commonly considered effects, including calibration errors, peculiar velocities, and local density variations are insufficient on their own to reconcile the reported values within quoted uncertainties. Several independent approaches corroborate the local H0 measurement. Gravitational lensing time delays, where multiple images of a distant quasar are deflected by an intervening galaxy, allow the calculation of absolute distances and expansion rate. The H0-Likau collaboration, analyzing 6 lensed quasars with extensive monitoring, obtained H0 values around 73 km per second per megaparsec. Surface brightness fluctuations in elliptical galaxies, maser distances, and tip-of-the-red giant branch measurements consistently indicate a higher local expansion rate than inferred from the early universe. These concordant results from different methodologies demonstrate that the tension is neither an artifact of a single method nor a trivial measurement error. Exploring the causes of the Hubble constant discrepancy requires understanding the underlying assumptions of each method. Early universe H0 depends heavily on parameters like baryon density, dark matter density, neutrino species, and the primordial helium fraction. Tiny changes in these values propagate through cosmological models, significantly affecting inferred expansion rates. Conversely, local H0 measurements rely on direct distance determinations corrected for metallicity, dust extinction, stellar age, and host galaxy environment. The sophistication and volume of modern datasets have minimized statistical uncertainty, but subtle systematic effects, if unrecognized, could still influence results. Current research involves cross-calibrating multiple indicators, applying homogeneous corrections, and testing consistency across independent surveys to isolate potential biases. Measurements of H0 have changed in parallel with developments in observational techniques and calibration methods. Early estimates near 500 km per second per megaparsec were revised following improvements in stellar classification and distance scaling, including Barde's recalibration and later results from the Key project. Advances in photometry, spectroscopy, statistical analysis, and telescope design have progressively reduced uncertainties and altered inferred values. These changes reflect the sensitivity of H0 determinations to both observational capabilities and underlying astrophysical assumptions. The Hubble constant is measured using a range of observational techniques, including Cepheids, type Ia supernovae, gravitational lensing time delays, and cosmic microwave background anisotropies. These methods probe different physical scales and epochs of the universe and yield systematically different values of H0. The resulting discrepancy has been identified across multiple independent datasets and observational approaches. Ongoing observational programs and theoretical analyses continue to quantify and compare these measurements under consistent methodological frameworks. Cepheid stars and the local universe. Resolving the disagreement over the expansion rate requires close inspection of the measurements that anchor the local universe, and among these, Cepheid variable stars occupy a central role. These stars are not simply convenient tools, but carefully studied physical systems whose behavior links observable properties to intrinsic luminosity. Because they sit near the base of the local distance framework, any systematic effect associated with Cepheids propagates upward into nearly every local measurement of the Hubble constant. For this reason, Cepheids have become one of the most intensely scrutinized objects in modern observational cosmology. Cepheid variables are pulsating supergiant stars whose brightness rises and falls in a regular, repeating pattern. Their defining feature is a tight relationship between pulsation period and intrinsic luminosity. Longer period Cepheids are intrinsically brighter than shorter period ones. This relationship allows astronomers to determine a Cepheid's true luminosity by measuring how long it takes to complete a pulsation cycle, which can range from a few days to over 100 days. Comparing intrinsic luminosity to observed brightness then yields distance. The underlying physics of this relationship is well understood and rooted in stellar structure, involving the partial ionization of helium in the star's outer layers, which drives rhythmic expansion and contraction. Cepheids are especially valuable because they are luminous enough to be observed in galaxies tens of megaparsecs away. Individual Cepheids can reach luminosities tens of thousands of times greater than the Sun, making them detectable with space-based telescopes, even in crowded galactic environments. This places them in an ideal position to bridge the gap between geometric distance measurements within the Milky Way and the distances to galaxies that host Type Ia supernovae. In practice, Cepheids form the critical calibration link between local stellar physics and the extragalactic distance scale. Modern Cepheid measurements rely heavily on data from the Hubble Space Telescope. Beginning in the 1990s and continuing through multiple instrument upgrades, HST enabled astronomers to resolve Cepheids in galaxies well beyond the local group. Programs such as the HST Key project and later the SH0ES program systematically observed Cepheids in galaxies that had also hosted well-measured Type Ia supernovae. By the early 2020s, over 1,200 Cepheids had been analysed across more than 70 galaxies, spanning distances up to roughly 40 megaparsecs. These datasets form the backbone of local Hubble constant measurements. Calibration is the most sensitive step in this process. Cepheid distances depend on accurately knowing the 0 point of the period luminosity relationship. This 0 point is established using Cepheids whose distances are known independently, primarily through geometric methods. The most important of these anchors include parallax measurements from the Gaia mission, Cepheids in the Large Magellanic Cloud, and Cepheids in the galaxy NGC 4258, whose distance is determined using water megamasers orbiting its central black hole. Each anchor provides an independent calibration, reducing reliance on any single assumption. The Large Magellanic Cloud plays a particularly important role. Located about 50 kiloparsecs from the Milky Way, it hosts thousands of Cepheids with a wide range of pulsation periods. Its relative proximity allows for precise photometry and detailed studies of Cepheid behavior. In 2019, a major analysis combining detached eclipsing binary measurements with Cepheid observations pinned the distance to the Large Magellanic Cloud to within about 1% uncertainty. This improvement significantly tightened the Cepheid calibration and reduced one of the dominant sources of systematic error in local expansion measurements. Gaia's contribution has been equally transformative. Its second and third data releases provided parallax measurements for hundreds of Milky Way Cepheids, many with distance uncertainties below 5% and some approaching 1%. These geometric distances allow the period luminosity relationship to be calibrated directly within the Milky Way, bypassing intermediate assumptions. While Gaia data initially revealed small tensions with earlier Cepheid calibrations, subsequent refinements in parallax 0-point corrections reduced these discrepancies and brought the results into closer numerical agreement. Despite these advances, Cepheid measurements are not free from complications. One persistent concern is the effect of metallicity, the abundance of elements heavier than helium in a star. Cepheids in different galaxies can have significantly different metallicities, which can subtly alter their luminosities at a given pulsation period. Observationally, metallicity differences between Cepheids in the Milky Way, the Large Magellanic Cloud, and more distant spiral galaxies can reach factors of 2. Modern analyses incorporate explicit metallicity corrections, typically finding that luminosity changes by a few percent per dex in metallicity. While important, these corrections are too small to account for the full Hubble tension. Interstellar dust introduces another layer of complexity. Dust absorbs and scatters light, making stars appear dimmer and redder than they truly are. Cepheids often reside in star-forming regions rich in gas and dust, particularly in spiral galaxies. To mitigate this effect, astronomers observe Cepheids in multiple wavelengths, including near-infrared bands, where dust extinction is significantly reduced. Infrared observations with HST and later the James Webb Space Telescope have further minimized dust-related uncertainties, leading to distance estimates that are more robust than earlier optical-only measurements. Crowding and blending also demand careful treatment. In distant galaxies, individual Cepheids may lie close to other stars in the sky, causing their light to overlap in telescope images. If uncorrected, this blending can artificially increase apparent brightness and bias distances. High-resolution imaging from space, combined with sophisticated point-spread function modeling, has largely mitigated this issue. Artificial star tests, in which simulated stars are injected into images and recovered using the same analysis pipeline, allow researchers to quantify and correct for residual crowding effects at the percent level. One of the most striking features of Cepheid-based measurements is their internal consistency. Different research teams, using different calibration anchors, photometric pipelines, and statistical treatments, consistently recover similar Cepheid distances. When these distances are combined with supernova measurements to infer the Hubble constant, the resulting values cluster tightly around 72 to 74 km per second per megaparsec. This convergence persists even when subsets of Cepheids are excluded, alternative anchors are emphasized, or different wavelength bands are used. The robustness of Cepheid results is further supported by cross-checks with other local distance indicators. In galaxies where both Cepheid and tip-of-the-red giant branch distances are available, the two methods generally agree within their quoted uncertainties. While the tip-of-the-red giant branch method tends to yield slightly lower Hubble constant values than Cepheids, the difference is typically only a few percent and does not erase the tension with early universe measurements. Importantly, Cepheids and red giant branch stars rely on entirely different stellar physics, making their agreement a powerful validation of local distance estimates. Cepheid measurements have also benefited from time domain surveys that extend over many years. Long-term monitoring allows precise determination of pulsation periods and identification of potential anomalies such as period changes or irregular variability. These effects are rare but detectable in high-quality datasets. Removing anomalous stars has a negligible impact on inferred distances, indicating that Cepheid samples are not dominated by pathological cases. As datasets have grown, statistical uncertainties in Cepheid distances have dropped to the level of 1 to 2%. At this precision, the dominant uncertainties are systematic rather than random. Extensive efforts have been made to quantify these systematics, including blind analyses in which calibration choices are fixed before examining their impact on the Hubble constant. These studies consistently find that reasonable variations in assumptions shift H0 by at most 1 to 2 km per second per megaparsec, far less than required to reconcile local and early universe values. As Cepheid observations have improved, their inferred distances have not shown a systematic drift toward lower expansion rates. Over time, the central value of the locally inferred Hubble constant has remained approximately constant, while statistical uncertainties have decreased. Analyses examining potential sources of systematic error have not identified effects large enough to shift Cepheid-based distances by the amount required to match early universe estimates. Cepheids connect geometric distance measurements, stellar astrophysics, and type Ia supernova calibration within the local distance framework. Their use spans multiple galaxies, instruments, and calibration anchors, including parallaxes, maser distances, and eclipsing binaries. As a result, Cepheid-based distances play a central role in establishing the local expansion rate used in comparisons with early universe measurements. Cepheid distances set the absolute luminosity scale for type Ia supernovae, enabling expansion measurements to be extended to much larger distances. Supernova-based distances inherit the calibration established by Cepheids and propagate it to galaxies well beyond the local universe. Analyses of the Hubble constant therefore examine how Cepheid-calibrated supernova distances compare with early universe inferences across increasing cosmic scales, type Ia supernovae, and the distance ladder. Once Cepheid variables establish distances to nearby galaxies, the expansion measurement depends on extending that scale far beyond the local universe. This next step is carried almost entirely by type Ia supernovae, stellar explosions so luminous they can be observed across billions of light years. Their role is not optional or peripheral. Without them, the distance framework would collapse beyond a few tens of megaparsecs. The reliability of local expansion measurements therefore hinges on whether these explosions behave consistently enough to serve as accurate distance markers once they are calibrated using Cepheids. Type Ia supernovae arise from white dwarf stars, the dense remnants of sun-like stars that have exhausted their nuclear fuel. In the most widely accepted scenario, a white dwarf in a binary system accretes matter from a companion star until it approaches a critical mass threshold. At that point, runaway nuclear fusion ignites nearly simultaneously throughout the star, releasing an enormous amount of energy and unbinding the white dwarf in a matter of seconds. The explosion briefly rivals the brightness of an entire galaxy, reaching peak luminosities of roughly 5 billion times that of the Sunday. What makes Type Ia supernovae useful for distance measurement is not that they are perfectly identical, but that their intrinsic variations follow predictable patterns. Observationally, brighter Type Ia supernovae decline more slowly after peak brightness, while dimmer ones fade more rapidly. This empirical relationship, first quantified in the early 1990s by Mark Phillips, allows astronomers to standardize supernova brightness by measuring how their light curves evolve over time. Once corrected for this effect, the scatter in intrinsic luminosity drops to about 10%, and with further refinements, to closer to 7%. The calibration of this standardized brightness depends directly on Cepheid distances. Astronomers identify galaxies that have hosted both Cepheid variables and Type Ia supernovae. Cepheids provide the absolute distance to the host galaxy, while the observed brightness of the supernova establishes its true luminosity. By the early 2020s, over 40 such calibration galaxies had been analyzed in detail, forming the foundation of the modern supernova distance scale. These calibrated supernovae are then used to measure distances to thousands of more distant galaxies where Cepheids are too faint to observe. Large observational programs have dramatically expanded the supernova dataset. Surveys such as the Supernova Legacy Survey, the Sloan Digital Sky Survey Supernova Survey, the Carnegie Supernova Project, and later the Dark Energy Survey have collectively observed several thousand Type Ia supernovae across a wide range of redshifts. These surveys employ uniform observing strategies, automated discovery pipelines, and consistent data reduction methods to minimize systematic differences between samples. Modern supernova cosmology relies not on a handful of events, but on statistically robust populations. Correcting supernova observations involves accounting for several astrophysical effects. Dust extinction in the host galaxy can dim and redden supernova light, similar to its effect on Cepheids. Color corrections are applied using multiband photometry, often spanning optical and near-infrared wavelengths. Host galaxy properties also matter. Supernovae occurring in massive metal-rich galaxies tend to be slightly dimmer after standardization than those in lower mass hosts. This effect, known as the host mass step, is typically on the order of 0.05 magnitudes and is explicitly included in modern analyses. Time dilation due to cosmic expansion introduces another observable effect. Supernova light curves appear stretched in time at higher redshifts, consistent with relativistic predictions. This stretching is directly measured and corrected, and is quantitatively consistent with expectations based on cosmological redshift. The observed agreement constrains alternative explanations that do not involve metric expansion. As supernova datasets grew, so did scrutiny of potential systematics. One concern was whether the properties of type Ia supernovae evolve with cosmic time. Supernovae observed at redshifts of 0.5 or higher exploded when the universe was several billion years younger, in environments with different average metallicities and star formation rates. Extensive comparisons between low redshift and high redshift samples, however, show no evidence for evolution large enough to bias the Hubble constant by more than a few percent. Near-infrared observations, which are less sensitive to dust and population effects, further support this conclusion. The precision of supernova-based expansion measurements improved steadily through the 2000s and 2010s. By combining hundreds of low redshift supernovae with carefully calibrated distances, local measurements of the Hubble constant achieved uncertainties below 2%. When tied to Cepheid distances, these analyses yielded expansion rates near 73 km per second per megaparsec across successive data releases and methodological updates. Independent teams using different supernova compilations and light curve fitting algorithms reached similar numerical results. The SALT2 and MLCS2K2 fitting frameworks, while based on different statistical assumptions, produced nearly identical H0 values when applied to the same calibration data. Tests that remove individual supernovae, exclude specific host galaxies, or restrict samples to narrow redshift ranges produce changes that are small compared with the quoted uncertainties. Supernova measurements extend Cepheid calibrated distances to scales of several hundred megaparsecs. When calibrated using Cepheid distances, type Ia supernovae yield expansion rates that are similar across this extended range. The inferred Hubble constant does not show a systematic decrease with increasing distance within the redshift range probed by local supernova samples. The supernova distance scale has also been calibrated using alternative methods. In addition to Cepheids, some analyses use the tip of the red giant branch method to calibrate nearby supernova hosts. These studies typically yield Hubble constant values in the range of approximately 69 to 71 km per second per megaparsec. The numerical differences between Cepheid and red giant branch calibrated supernova distances are quantified and incorporated into comparative analyses. Gravitational wave observations provide an independent distance measurement method. The detection of a binary neutron star merger in 2017, accompanied by an electromagnetic counterpart, allowed a direct distance measurement using gravitational waves and redshift from the host galaxy. This standard siren measurement yielded a Hubble constant estimate with large statistical uncertainty due to limited event counts. Additional detections will improve the statistical precision of this approach. Supernova samples distributed across the sky show no statistically significant directional dependence in the Hubble constant at the percent level. Measurements corrected for peculiar velocities derived from galaxy density fields reduce residual scatter in inferred expansion rates. The mean Hubble constant value remains unchanged within uncertainties after these corrections. Early supernova measurements in the late 1990s were based on small samples and large uncertainties. Over subsequent decades, improvements in instrumentation, calibration procedures, and statistical modeling increased sample sizes and reduced uncertainties by approximately a factor of 4. Across these developments, reported supernova-based H0 values remained within a similar numerical range. Analyses have examined potential sources of systematic error in supernova physics, Cepheid calibration, and related cross-checks. No identified effect has been shown to shift supernova-based distances by the magnitude required to reconcile local measurements with early universe estimates. Studies continue to evaluate possible correlated systematics across multiple datasets. Type Ia supernovae extend Cepheid-calibrated distance measurements to volumes containing tens of thousands of galaxies. These measurements probe expansion over scales well beyond the local universe. The resulting Hubble constant values are compared directly with estimates derived from early universe observations. Early universe probes infer the expansion rate indirectly from physical conditions encoded in the cosmic microwave background and other relic signals from the early universe. These methods differ fundamentally from distance-based measurements that rely on Cepheids and supernovae. Comparisons between the two approaches are used to quantify differences in inferred expansion rates. The cosmic microwave background's conflicting story. While Cepheids and supernovae trace the expansion of the universe by directly measuring distances and recession speeds, early universe observations infer expansion from conditions in the young universe. The cosmic microwave background, CMB, is a relic radiation field originating when the universe was approximately 380,000 years old, before the first stars or galaxies formed. Measurements of the CMB provide data on the temperature, density, and velocity distributions at that epoch, which can be used to estimate the present-day expansion rate when interpreted within a cosmological model. The cosmic microwave background, or CMB, originates from a time roughly 380,000 years after the Big Bang, when the universe cooled enough for protons and electrons to combine into neutral hydrogen. Before this epoch, photons were constantly scattered by free electrons, making the universe opaque. Once neutral atoms formed, photons began to travel freely through space, carrying with them information about the temperature, density, and motion of matter at that moment. Today, this radiation is observed as a nearly uniform microwave glow filling the sky, with an average temperature of approximately 2.725 Kelvin. Although the CMB appears smooth at first glance, precise measurements reveal tiny temperature variations at the level of tens of microkelvin. These fluctuations are not random noise. They reflect sound waves that propagated through the hot plasma of the early universe, driven by the competing effects of gravity and radiation pressure. Regions slightly denser than average attempted to collapse under gravity, while radiation pressure resisted that collapse, producing oscillations whose characteristic scales were frozen into the CMB when photons decoupled from matter. The angular size of these fluctuations on the sky encodes critical cosmological information. In particular, the scale of the first acoustic peak corresponds to the maximum distance sound waves could have traveled before recombination. This physical scale depends on conditions in the early universe, including the density of ordinary matter, dark matter, and radiation. The angle under which this scale is observed today depends on the geometry of space and the integrated expansion history between recombination and the present. By measuring this angle with high precision, cosmologists can infer how the universe expanded over nearly its entire lifetime. The first detailed measurements of the CMB came from the COBE satellite in the early 1990s, which confirmed the existence of temperature fluctuations. Subsequent missions dramatically improved precision. The Wilkinson Microwave Anisotropy Probe, operating from 2001 to 2010, mapped the full sky with angular resolution down to about 0.2 degrees. Its results established the basic parameters of the standard cosmological model with unprecedented clarity. However, it was the Planck satellite, launched by the European Space Agency in 2009, that transformed the CMB into a precision instrument for cosmology. Planck measured temperature fluctuations across the sky with angular resolution better than 5 arc minutes and polarization fluctuations with similarly high sensitivity. By the time its final data release appeared in 2018, Planck had measured the positions and heights of multiple acoustic peaks with extraordinary accuracy. These data constrained key cosmological parameters to percent-level precision or better. When analyzed within the standard lambda-cold dark matter framework, the Planck data implied a Hubble constant of approximately 67.4 km per second per megaparsec with an uncertainty of less than 1%. The CMB does not measure the Hubble constant directly. Instead, it constrains a set of early universe parameters, including the densities of baryons and dark matter, the spectral index of primordial fluctuations, and the optical depth to reionization. The present-day expansion rate is derived by evolving these parameters forward in time using the equations of cosmic expansion. The inferred Hubble constant depends on the adopted cosmological model. Independent subsets of the Planck data, including temperature-only measurements, polarization-only measurements, and cross-correlations between them, converge on similar parameter values. Analyses using different foreground removal techniques and likelihood constructions yield comparable results. Planck's measurements also align with those from WMAP, despite differences in instruments, observing strategies, and data analysis pipelines. The difference between the CMB inferred expansion rate and the Cepheid and supernova-based value exceeds approximately 5 km per second per megaparsec. In statistical terms, this corresponds to more than 4 standard deviations, depending on the datasets and assumptions used. This numerical difference is the basis for ongoing comparisons between early universe and local measurements. The sound horizon, the physical scale set by acoustic waves in the early universe, is tightly constrained by the CMB at recombination. Local measurements, extrapolated backward assuming the standard expansion history, imply a smaller sound horizon than that inferred from the CMB. Resolving this numerical difference requires adjustments to the inferred sound horizon or to the expansion history within the cosmological model. The CMB also provides information beyond temperature fluctuations. Polarization patterns, particularly the so-called E-mode polarization, offer an independent probe of early universe physics. These patterns arise from Thomson scattering of photons off electrons in the presence of quadrupole temperature anisotropies. Planck's polarization data reinforce the temperature-based conclusions, yielding nearly identical constraints on the Hubble constant. The consistency between temperature and polarization measurements further strengthens confidence in the early universe result. Foreground contamination has been examined extensively as a potential source of bias. Emission from dust within the Milky Way, synchrotron radiation from charged particles spiraling in magnetic fields, and extragalactic radio sources all contribute signals that must be separated from the primordial CMB. Planck observed the sky in 9 frequency bands, ranging from 30 to 857 GHz, specifically to disentangle these effects. Independent component separation methods, such as SMICA, NILC, and CVEM, produce consistent cosmological parameters, indicating that foregrounds are not driving the expansion discrepancy. Instrumental systematics have also been scrutinized. Planck's detectors were calibrated using the well-understood dipole anisotropy caused by Earth's motion relative to the CMB rest frame. Beam shapes, noise properties, and time-dependent detector effects were modeled in detail. Extensive null tests, in which data are split by time, detector set, or observing strategy, show no evidence of anomalies capable of shifting the inferred Hubble constant by the required amount. Measurements of baryon acoustic oscillations in the distribution of galaxies provide an independent constraint on the sound horizon. When combined with primordial element abundances inferred from Big Bang nucleosynthesis, these data yield expansion rate estimates that are consistent with CMB-derived values when analyzed within the standard cosmological framework. Attempts to extract a higher Hubble constant from the CMB alone have largely failed. Allowing additional freedom in parameters such as the effective number of relativistic particle species or the primordial helium fraction can shift the inferred expansion rate slightly upward, but typically at the cost of degrading the fit to other aspects of the data. In many cases, such modifications introduce new tensions with independent observations, limiting their viability as simple fixes. The CMB reflects conditions when the universe was comparatively simple and well described by linear physics, unlike local measurements that are affected by dust, stellar evolution, and galaxy environments. Its interpretation depends on assumptions about the contents and dynamics of the universe, which are incorporated into the cosmological model. Local measurements based on Cepheids and supernovae yield Hubble constant estimates, while CMB observations provide derived expansion rates within a cosmological model. Both methods produce internally consistent results within their respective datasets. The numerical difference between these two sets of measurements represents the current discrepancy in expansion rate estimates. Researchers have examined how assumptions in the standard cosmological model influence derived expansion rates from the CMB. Small changes to early universe parameters at different epochs can affect the present-day Hubble constant inferred from the data. Translating early universe measurements into present-day cosmological parameters requires analyzing the structure and assumptions of the cosmological model. This process quantifies how variations in model parameters affect the inferred expansion rate, Planck, WMAP, and the early universe assumption. While Cepheids and supernovae provide measurements of the local universe, satellites like the Wilkinson Microwave Anisotropy Probe, WMAP, and Planck observe the cosmic microwave background, CMB, the relic radiation from the Big Bang, approximately 380,000 years after the event. Fluctuations in the CMB carry information about baryon density, dark matter fraction, acoustic oscillation scales, and parameters related to the universe's expansion. Cosmologists use these measurements within the LCDM framework to calculate the Hubble constant. WMAP, launched in 2001, marked the first mission capable of mapping the CMB with high angular resolution across the full sky. Its 9-year data release provided measurements of temperature anisotropies with precision approaching 1 part in 100,000. By analyzing the relative heights and positions of acoustic peaks, WMAP constrained the density of ordinary matter to roughly 4.6% of the critical density and dark matter to 22.7%, with the remaining 72.7% attributed to dark energy in the WCDM framework. Using these parameters, the inferred Hubble constant was 69.3 plus or minus 1.5 kilometers per second per megaparsec, a value slightly higher than the Planck result that would follow, but still lower than local Cepheid-based measurements. Planck, launched in 2009, dramatically improved upon WMAP's precision. With higher angular resolution and sensitivity, Planck mapped temperature and polarization fluctuations down to scales of 5 arc minutes, providing a detailed view of the CMB that had been unattainable from previous missions. Planck's measurements of the first 6 acoustic peaks allowed cosmologists to determine cosmological parameters with unprecedented accuracy. Baryon density at 4.9%, dark matter density at 26.3%, and dark energy at 68.8% of the critical density. Combining these measurements with the WCDM model produced a predicted Hubble constant of 67.4 plus or minus 0.5 kilometers per second per megaparsec. The uncertainty here is remarkably small, yet it sits in stark contrast with the local value of 73 kilometers per second per megaparsec, highlighting the growing tension between early and late universe determinations. Extracting H0 from the CMB is not a direct measurement. Unlike Cepheids, which provide a physical distance through observed brightness, the Hubble constant from the CMB emerges from a model-dependent inference. Cosmologists take the observed angular size of acoustic peaks, essentially, the sound horizon, at recombination, and divide it by the predicted physical size, which depends on the total matter content, dark energy fraction, radiation density, and even the number of relativistic neutrino species. Small changes in these parameters ripple through the model, affecting the inferred expansion rate today. The precision of Planck is such that even sub-percent variations in baryon density or neutrino mass can shift the predicted H0 by several kilometers per second per megaparsec. Both WMAP and Planck analyses use the WSCDM model, which treats dark energy as a cosmological constant, assumes general relativity applies universally, and considers the universe homogeneous and isotropic on large scales. The CMB measurements provide information about the early universe, and the Hubble constant is inferred by evolving these parameters forward using WCDM. The inferred H0 depends on the assumptions of the model. Planck's dataset allowed for multiple checks within the early universe framework. Multiple frequency channels enabled separation of foreground contamination from galactic dust and synchrotron emission. Polarization data cross-checked temperature anisotropies, and lensing of the CMB by large-scale structures provided an additional test. These methods help ensure that systematic errors in the instrument or analysis do not significantly bias the inferred Hubble constant. WMAP and Planck data show that early universe parameters influence the inferred Hubble constant. The effective number of neutrino species, NEF, changes the expansion rate before recombination, affecting the angular size of the sound horizon. The primordial helium fraction alters the electron density, influencing photon diffusion and peak amplitudes in the CMB power spectrum. Variations in these parameters within observational limits can shift the inferred H0 by a few percent. Planck and WMAP data show that inferred H0 depends on the chosen cosmological model. Alternative models, such as those including early dark energy or modified gravity, can change the predicted Hubble constant without conflicting with CMB measurements. In LCDM, parameters are interdependent. Changes to dark matter fraction require adjustments in baryon density, curvature, or dark energy to match observed peak heights and positions. Planck data provide highly precise H0 estimates based on early universe observations. Despite observing photons emitted nearly 14 billion years ago, Planck predicts H0 to a fraction of a percent. The precision of these estimates highlights differences between early universe and local measurements, which remain above the uncertainty limits of both datasets. WMAP and Planck data can be cross-checked with independent datasets. Combining CMB measurements with baryon acoustic oscillations, or BAO, provides a test for the inferred sound horizon. When analyzed jointly, BAO data produce H0 estimates consistent with CMB-derived values. Similarly, gravitational lensing of the CMB by large-scale structures yields mass distribution estimates consistent with Planck's parameters. The determination of H0 from the early universe depends on model assumptions. Unknown physics prior to recombination, such as additional relativistic species, non-standard interactions, or early dark energy, could alter the inferred H0 without affecting the measured acoustic peaks. Researchers simulate small deviations from WCDM to evaluate how parameter changes influence the present-day expansion rate. To date, no tested modification fully resolves the numerical difference between early universe and local H0 estimates. Planck and WMAP provide precise H0 estimates, with precision dependent on assumptions about cosmic history, particle physics, and dark energy. Comparison with local measurements shows a numerical difference that exceeds the combined uncertainties of the datasets. The interpretation of the CMB relies on the cosmological model used, and alternative model choices can change the inferred H0. When precision makes the problem worse, in the quest to measure the universe's expansion, the development of ever more precise instruments was expected to resolve lingering uncertainties. Instead, it intensified the mystery. As astronomers refined their tools and techniques, systematic errors shrank, datasets grew, and statistical uncertainties fell. Yet the tension between local and early universe measurements of the Hubble constant only became more pronounced. Far from providing clarity, precision revealed a divergence too persistent and too systematic to ignore. Space-based observatories and advanced ground-based surveys transformed observational cosmology into a field of exceptional accuracy. The Hubble Space Telescope continued to expand its Cepheid sample, while missions like Gaia refined parallax measurements to micro-arcsecond precision for over 1 billion stars. Instruments, such as the Keck Observatory's Deimos spectrograph, measured galaxy velocities with a few kilometers per second uncertainty, and the Dark Energy Camera at Cerro Tololo mapped millions of galaxies in unprecedented detail. Each technological advance reduced random scatter and improved calibration, leaving no room for the kinds of errors that once explained minor discrepancies. Yet rather than converging toward a single H0 value, the gap widened. The SH0ES collaboration, now analyzing more than 1,500 Cepheids across 75 galaxies, consistently reported 73.2 plus or minus 1.1 kilometers per second per megaparsec. Simultaneously, the Planck team, after incorporating the full mission's temperature and polarization data, produced 67.4 plus or minus 0.5 kilometers per second per megaparsec. The difference over 5 kilometers per second per megaparsec represents nearly a 10% divergence and exceeds 5 standard deviations, a level of statistical significance that would be considered decisive in virtually any other branch of physics. As uncertainties in H0 measurements decreased, the numerical difference between local and early universe values became more apparent. Overlapping error bars were no longer present, and random noise, calibration issues, or misestimated peculiar velocities could not fully account for the discrepancy. Several developments illustrate how precision intensified scrutiny. In 2016, Reis and colleagues introduced a uniform photometric calibration across all Cepheid observations, correcting for metallicity, crowding, and dust extinction more rigorously than in previous studies. Their results held the local H0 value remained high. Around the same time, Tip of the Red Giant Branch, or TRGB distance measurements, led by Wendy Friedman and collaborators, provided an independent calibration for nearby galaxies. The TRGB-based H0 estimate fell slightly lower, near 70 kilometers per second per megaparsec, but still failed to reconcile with Planck. Similarly, gravitational lensing time delays, analyzed by the H0 Lykow team, produced H0 values around 72 kilometers per second per megaparsec. Multiple independent approaches were converging on a local universe expansion rate that remained stubbornly high. Meanwhile, early universe estimates continued to grow in precision. The Planck mission's final 2018 release combined temperature, polarization, and lensing data, achieving percent-level uncertainties in parameters such as baryon density, dark matter fraction, and scalar spectral index. These parameters dominate the predicted H0. Any attempt to reconcile early universe H0 with local measurements within the standard LCDM framework runs into immediate tension. Adjusting one parameter to raise H0 disrupts the fit to acoustic peak heights or shifts the predicted matter density beyond observed limits. The very precision of Planck constrains flexibility, making the discrepancy harder to dismiss. Cosmic chronometers, stellar populations used to estimate the universe's age at different redshifts, suggest different ages depending on the H0 value used. Local H0 measurements imply a slightly younger universe, while CMB-based H0 implies an older one. Large-scale structure studies and baryon acoustic oscillations, which probe expansion across hundreds of millions of light-years, produce H0 values closer to early universe estimates. The increased precision also forced cosmologists to re-evaluate sources of potential systematic error that had once been assumed negligible. For Cepheids, this meant scrutinizing host galaxy properties, metallicity gradients, and the impact of crowding in crowded star fields. For supernovae, teams examined progenitor populations, explosion asymmetries, and light curve modeling. For CMB analysis, researchers accounted for instrumental beam profiles, polarized foreground emission, and subtle lensing effects. Each layer of correction improved internal consistency, but did not resolve the fundamental H0 tension. When the Hubble constant's uncertainty was roughly plus or minus 10 km per second per megaparsec, the SH0 ES and Planck results overlapped within 2 sigma. With improved calibrations, SH0 ES uncertainties dropped below plus or minus 1.2 km per second per megaparsec, and Planck below plus or minus 0.5. The remaining 5 km per second difference now corresponds to more than 5 sigma, indicating that random chance or small errors cannot explain the discrepancy. Another consequence is the cross-validation of methods. Surface brightness fluctuations in elliptical galaxies, maser distances in galaxies like NGC 4258, and time delay lenses have all become precise enough to weigh meaningfully against CMB predictions. None fully aligns with Planck, all reinforce the existence of a genuine tension. Researchers like Lucas Macri and Sherry Suyu emphasize that this convergence of independent methods suggests the discrepancy is not an artifact of a single instrument, team, or technique, but a real feature of the cosmos. Planck's polarization measurements allowed mapping of reionization and early matter clustering, while Gaia's parallax data identified small gradients in the Milky Way that could bias local calibrations by a fraction of a percent. These systematic effects are smaller than the 5 km per second difference in H0 and do not resolve the discrepancy. As measurement precision improved, the numerical difference between local and early universe H0 values became more pronounced. Each refined measurement and reduced uncertainty consistently shows that local and early universe expansion rates differ. If the difference between local and early universe H0 persists, it may indicate either an unrecognized systematic error in one or more measurement techniques or incomplete assumptions in WCDM. Further measurements could help identify which parameters or processes influence the discrepancy, including potential effects from dark energy, neutrinos, or the early universe energy content. Increasing measurement precision has highlighted the difference between local and early universe H0 values. As observational campaigns continue and next-generation instruments provide tighter constraints, the difference between the two H0 estimates remains measurable and statistically significant. Independent methods that should have settled it. If the growing tension in the Hubble constant seemed like a problem confined to Cepheids, supernovae, or the cosmic microwave background, independent methods promised a decisive verdict. In principle, gravitational lensing, maser galaxies, and surface brightness fluctuations offered ways to measure cosmic distances and expansion rates without relying on traditional distance ladders or early universe assumptions. By the mid-2010s, cosmologists anticipated that these alternative techniques would confirm one side of the debate and restore coherence. Instead, they deepened the mystery and, in some ways, made the discrepancy more pronounced. Gravitational lensing time delays provide one of the most compelling independent tests. When a massive galaxy lies along the line of sight to a distant quasar, its gravity bends light into multiple images. Light traveling along each path reaches Earth at slightly different times. By monitoring brightness variations in these quasar images over months and years, astronomers can calculate the light travel time differences, which depend directly on absolute distances and the expansion rate. This method is sensitive to the mass distribution of the lensing galaxy and the geometry of the system, but it does not rely on assumptions about the intrinsic luminosities of stars or the cosmic microwave background. The H0 LICAO collaboration, led by Sherry Suyu, meticulously tracked 6 lensed quasars, combining high-resolution imaging from the Hubble Space Telescope with spectroscopy from the Keck Observatory and the Very Large Telescope. The resulting H0 estimate averaged 72.5 plus or minus 2.1 kilometers per second per megaparsec, aligning closely with the local Cepheid-based value. The precision of gravitational lensing measurements improved dramatically with adaptive optics and long-term monitoring. For example, the lens system RxJ 113-11231 was observed over 9 years with the Gemini North Telescope, yielding time delays measured to better than 1% accuracy. Similarly, the quasar HE04351223 produced H0 estimates between 71.6 and 73 kilometers per second per megaparsec, depending on the mass model of the lensing galaxy. These measurements demonstrated that even with varying assumptions about lens profiles, whether singular isothermal ellipsoids or power law distributions, the inferred Hubble constant consistently favored the higher local rate. Water megamasers in accretion disks around supermassive black holes provide another geometric distance measurement entirely independent of Cepheids or supernovae. In galaxies such as NGC 4258, maser clouds orbit the central black hole at precisely measurable velocities, and by mapping their rotation using very long baseline interferometry, astronomers can derive distances with accuracies of 2 to 3%. Reed, Humphreys, and collaborators reported H0 values near 72 kilometers per second per megaparsec from NGC 4258, while similar observations in UGC 3789 and NGC 6264 reinforced the result. These galaxies are located between 7 and 140 megaparsecs, spanning the transition from local to intermediate distances. Because masers trace orbital mechanics around a well-understood gravitational center, this technique is largely immune to the systematic errors that can affect standard candles, such as metallicity or interstellar extinction. Surface brightness fluctuations in elliptical galaxies provide yet another alternative. This method leverages the fact that stars in a galaxy are not distributed perfectly smoothly. The statistical variation in brightness between pixels in high-resolution images diminishes with distance, offering a standard ruler on galaxy scales. Observations using the HST and ground-based telescopes, led by John Tonry, Michael Blakesley, and Stefano May, measured distances to dozens of galaxies in the Virgo, Fornax, and Coma clusters. These measurements produced H0 values consistently between 70 and 74 kilometers per second per megaparsec. While this technique is sensitive to stellar population characteristics such as age and metallicity, careful modeling mitigates most biases, again pointing toward a higher local expansion rate. Each of these independent approaches has distinct assumptions and potential sources of error. Lensing measurements depend on mass modeling of the lensing galaxy. Maser distances require precise orbital mapping, and surface brightness fluctuations are sensitive to the underlying stellar population. Across these methods, reported H0 values are generally consistent with the higher local rate. Further intricacies emerge when examining individual datasets. Gravitational lensing estimates vary slightly depending on assumptions about dark matter halo profiles, with individual quasars producing H0 estimates ranging from 70 to 75 km per second per megaparsec. In maser cosmology, while NGC 4258 provides one of the most precise distances, the sample of suitable galaxies is small, limiting statistical weight. Yet even with this limitation, the results are broadly compatible with higher local H0 values. Surface brightness fluctuation distances can shift by 1 to 2% depending on calibration choices, filter bandpasses, or galaxy selection criteria. When combined across different clusters, however, they still consistently indicate a faster expansion locally than early universe measurements suggest. Observations of giant H2 regions, the brightest star-forming regions in nearby galaxies, provide a luminosity-based distance measurement separate from Cepheids or TRGB stars. Investigators such as Ricardo Chavez and Enrique Perez Montero applied H2 region measurements to galaxies like M101, NGC 300, and NGC 2403, producing H0 values around 71 km per second per megaparsec. Tip of the red giant branch measurements, calibrated with Gaia parallaxes, led by Wendy Friedman, Lucas Macri, and Barry Mador, yield H0 estimates around 70.2 km per second per megaparsec, above the Planck value of 67.4 km per second per megaparsec. Observations extending geometric and lensing techniques beyond the local universe provide additional insight. For example, the megamaser galaxy NGC 5765b, located roughly 133 megaparsecs away, and UGC 3789 at 120 megaparsecs, allowed direct measurements overlapping the regime where peculiar velocities are expected to average out. Both produced H0 values exceeding 71 km per second per megaparsec, demonstrating that the higher local expansion rate is not confined to the immediate cosmic neighborhood. Similarly, gravitational lensing systems such as SDSS 1000, 206 plus 4000, 332, HE11041805, and PG115 plus 080, when modelled with detailed stellar kinematics and multiband imaging, provide consistent H0 estimates above 72 km per second per megaparsec. Each independent method uses different physics, wavelengths, distances, and observational strategies. Gravitational lensing uses light deflection and general relativity. Masers exploit orbital dynamics around supermassive black holes. Surface brightness fluctuations rely on stellar statistics, and H2 regions depend on emission line luminosities. Measured H0 values from these techniques are generally higher than early universe predictions. Even within these techniques, small discrepancies reveal physical and observational challenges. Lensing H0 values can vary by a few kilometers per second per megaparsec, depending on lens ellipticity, external shear, or the inclusion of nearby perturbers. Maser distances are constrained by the number of detectable systems, orbital inclination uncertainties, and long-term monitoring requirements. Surface brightness fluctuation results depend on bandpass selection, age metallicity calibrations, and the presence of intermediate age stellar populations. Reported H0 values from these methods generally remain within the range of local, Cepheid, and supernova measurements. Taken together, these independent measurements provide multiple methods to estimate H0 without relying on Cepheids or early universe assumptions. Each technique produces H0 values generally in the range of 70-74 kilometers per second per megaparsec, above the Planck value of 67.4 kilometers per second per megaparsec. The discrepancy is observed across multiple independent methods and datasets, large-scale structure, and galaxy clustering. While local measurements of the Hubble constant suggest a faster expansion rate, cosmologists have investigated the universe on larger scales. Beyond individual stars, supernovae, and gravitational lenses lies the cosmic web, a network of galaxies, filaments, voids, and clusters spanning billions of light-years. The arrangement of this large-scale structure encodes expansion history, influenced by dark matter, dark energy, and gravity. Mapping and analyzing galaxy distributions allows independent estimates of the Hubble constant that do not rely on local calibration methods. One of the most influential tools in this effort is the study of baryon acoustic oscillations, or BAR. These are subtle, primordial sound waves that propagated through the hot plasma of the early universe, leaving faint imprints on the distribution of matter. When the universe cooled and neutral atoms formed, these oscillations became frozen into the large-scale clustering of galaxies. The characteristic scale imprinted by BAO acts as a cosmic yardstick. Measuring it at different redshifts allows cosmologists to infer distances and, by extension, the rate of expansion over cosmic time. The Sloan Digital Sky Survey, SDSS, first mapped these oscillations with high precision using over 930,000 luminous red galaxies across roughly 8,000 square degrees. Subsequent analyses by the Baryon Oscillation Spectroscopic Survey extended the dataset to 1.2 million galaxies out to redshift 0.7, providing a three-dimensional map of clustering that reaches hundreds of megaparsecs. Measurements of the scale of the acoustic peak in the correlation function of galaxies suggest a Hubble constant around 67-68 kilometers per second per megaparsec, depending on the assumed cosmological model. This is lower than local measurements derived from Cepheids, supernovae, or lensing. BAO operates at intermediate redshifts, roughly 1 to 4 billion years after the Big Bang, allowing researchers to track expansion evolution independently of nearby structures. Complementing BAO, galaxy redshift surveys provide additional insight into cosmic expansion. Projects such as the 2DF Galaxy Redshift Survey, SDSS, and the ongoing Dark Energy Spectroscopic Instrument Survey map the positions and velocities of millions of galaxies, revealing not only clustering patterns, but also anisotropies caused by peculiar velocities. Redshift space distortions, apparent elongations or compressions in clustering caused by galaxy motions, allow researchers to measure the growth rate of cosmic structures. For example, the 2DF survey, encompassing 221,000 galaxies, detected coherent infall velocities around massive clusters, constraining the combination of matter density and expansion. Similarly, BOSS analyses of over 1.4 million galaxies quantified the growth of structure with unprecedented precision, confirming predictions based on a lower Hubble constant. The clustering of galaxies is not random. Filaments connect clusters across tens of megaparsecs, while vast voids span hundreds of megaparsecs, regions almost entirely devoid of galaxies. Studies led by Rian van der Wegeert and Miguel Aragon Calvo have mapped these voids using SDSS data, revealing their volume fraction, shape distribution, and evolution over time. Voids expand slightly faster than the average universe due to their underdensity, but simulations show that their effect on H0 is modest, typically altering local measurements by only 1 to 2%. Even when accounting for a local void hypothesis, the clustering and void data continue to support the slower expansion indicated by early universe probes. Cluster abundance offers yet another window into the expansion history. Galaxy clusters are the largest gravitationally bound structures, and their number density, as a function of redshift, is sensitive to the Hubble constant, matter density, and dark energy. Surveys such as the South Pole Telescope, or SPT, and the Atacama Cosmology Telescope, or ACT, have catalogued thousands of clusters using the Sunyaev-Zeldovich effect, which measures distortions in the cosmic microwave background caused by hot intracluster gas. Combining these counts with X-ray data from Chandra and XMM Newton allows precise determination of cluster masses and distances. Results from these surveys, including the SPT cluster sample of 516 objects out to redshift 1.2, favor a Hubble constant closer to 68 km per second per megaparsec, again echoing the early universe value rather than the faster local measurements. Cross-correlating BAO with redshift space distortions, weak lensing measurements, and cluster counts produces H0 estimates, generally around 67-68 km per second per megaparsec. Weak gravitational lensing surveys, such as the Kilo Degree Survey and the Dark Energy Survey, measure distortions in the shapes of millions of background galaxies to map matter distribution. DES alone, observing 300 million galaxies across 5,000 square degrees, constrains the amplitude of matter fluctuations and the expansion history. These measurements remain consistent with the lower H0 values inferred from early universe probes. Complicating matters further, the scale dependence of clustering introduces subtle corrections. Nonlinear evolution in dense regions, galaxy bias, and baryonic feedback all influence observed correlation. Teams led by Martin White and Andrei Kravtsov have used high-resolution simulations, including Illustris TNG and Millennium Taptics L, to calibrate these effects, ensuring that measurements of the acoustic scale and growth rate are not biased by astrophysical processes. These studies reveal that even after accounting for complex clustering physics, the tension between local and large-scale H0 remains. Another avenue arises from peculiar velocity surveys, which track galaxy motions relative to the overall Hubble flow. Projects like 6DF, Cosmic Flows, and the Tully-Fisher survey use distances inferred from rotation speeds or other indicators to detect deviations caused by large-scale gravitational fields. While these motions can reach hundreds of kilometers per second, averaging across thousands of galaxies should eliminate local biases. Yet analysis by Brent Tully and Hélène Courtois indicates that even after accounting for local flows, the inferred H0 still lies below local Cepheid or supernova-based values, consistent with the BAO and cluster evidence. Combining different tracers over a wide redshift range, including BOSS at Z, is approximately equal to 0.57, DES at Z is approximately equal to 0.31, and KIDS weak lensing at Z is approximately equal to 0.4, 0.9, produces an H0 of roughly 67.8 plus or minus 1 km per second per megaparsec. H0 estimates from multiple instruments, wavelengths, and methodologies remain consistent across these datasets. Large-scale simulations allow cosmologists to explore whether cosmic variance or environmental effects could affect H0 measurements. Simulations spanning volumes exceeding a cubic gigaparsec, such as multidark and horizon AGN, model galaxy formation, clustering, and void evolution. Even when accounting for rare underdense or overdense regions, these simulations do not produce the roughly 6 km per second per megaparsec difference observed between local and large-scale measurements. Large-scale structure measurements, including BAO, redshift space distortions, weak lensing, and cluster abundances, produce H0 estimates generally around 67-68 km per second per megaparsec. These results are consistent across hundreds of megaparsecs and multiple datasets. Combined analyses of galaxy surveys, CMB-calibrated BAO, and weak lensing provide multiple independent estimates of cosmic expansion on large scales. dark energy's role under scrutiny. The accelerated expansion of the universe, first revealed in 1998 through observations of distant Type Ia supernovae, introduced dark energy as a component in cosmology. Initially treated as a constant, uniform energy density filling space, dark energy was incorporated into the WLCDM model as the cosmological constant. This addition reconciles observed acceleration with general relativity and the matter content of the universe. Recent measurements of cosmic expansion show differences between local Hubble constant values, clustering data, and early universe predictions, motivating the investigation of potential time variation in dark energy. Type Ia supernova surveys provide the foundation for understanding dark energy's effect on cosmic expansion. The Supernova Legacy Survey, or SNLS, the eSense Project, and the Pan-STARRS 1 Medium Deep Survey have collectively catalogued over 1,500 well-observed supernovae out to redshift 1.5. These explosions serve as standardizable candles, allowing astronomers to trace how the expansion rate has changed over the past 9–10 billion years. Analysis of these datasets indicates that dark energy has been dominant for roughly half the universe's lifetime. Yet subtle deviations from a purely constant density remain plausible. The Joint Light Curve Analysis dataset, which combined over 740 supernovae, hinted at a mild preference for a time-varying dark energy equation of state, although statistical significance remained low at about 1–2 sigma. Large galaxy surveys add further constraints. The Dark Energy Survey, observing 300 million galaxies over 5,000 square degrees, uses weak gravitational lensing and galaxy clustering to map the growth of structure. These measurements are sensitive to both the rate of expansion and the strength of gravity over cosmic time. DES Year 3 analyses report a matter density parameter of 0.31 plus or minus 0.01 and a dark energy equation of state W equals 1.02 plus or minus 0.04, consistent with a cosmological constant but leaving room for small deviations. Similarly, the Kilo Degree Survey, KIDS, and Hyper Supremecam, HSC, survey independently confirm W values close to 1, but with variations hinting at possible evolution. While supernovae and lensing surveys primarily probe the recent universe, cosmic microwave background observations provide a complementary perspective. Planck's 2018 results measured the CMB temperature and polarization anisotropies with high accuracy, constraining the combination of matter, radiation, and dark energy density. The inferred dark energy density fraction, omega W, is approximately equal to 0.684, assumes a cosmological constant. Small adjustments in early universe parameters, such as the effective number of neutrino species or the helium fraction, can shift inferred expansion histories. Attention has increasingly turned to early dark energy models, in which dark energy contributes a small but non-negligible fraction of the total energy density before recombination. Researchers including Vivian Poulin, Tristan Smith, and Will Handley have explored scenarios where dark energy comprises roughly 25% of the energy budget at Z is approximately equal to 3, enough to affect the sound horizon and thereby shift the inferred Hubble constant from CMB observations. Such models remain consistent with Planck's CMB power spectra, while potentially reconciling the higher H0 values from local measurements. Yet these proposals are tightly constrained by Big Bang nucleosynthesis, galaxy clustering, and BAO measurements, leaving only a narrow window of viability. Alternative approaches question whether dark energy is truly uniform or whether it varies spatially. Chameleon field theories and quintessence models developed by researchers such as Justin Cowrie, Lam Hui, and P.J.E. Peebles, allows the energy density of dark energy to evolve in response to local gravitational environments. Observational constraints from the Hubble Space Telescope and the Very Large Telescope's multi-unit spectroscopic explorer suggest that spatial variations, if they exist, must be smaller than 1% on scales of tens to hundreds of megaparsecs. Still, such mechanisms could, in principle, contribute to the persistent local versus large-scale H0 discrepancy. Direct measurements of cosmic expansion, independent of distance ladders, provide data on dark energy's effects. Cosmic chronometers' massive, passively evolving galaxies with well-understood stellar populations allow determination of the Hubble parameter by measuring differential aging across redshifts. Observations by Raúl Jiménez, Licia Verde, and colleagues using galaxies from the Sloan Digital Sky Survey and Gemini Observatory have yielded hazard values between 65 and 85 kilometers per second per megaparsec across redshifts 0.12. Individual measurement uncertainties remain at 5–10%. Gravitational lensing time delays provide another measurement of cosmic expansion. The H0 Lykow collaboration analyzed 6 strongly lensed quasars, measuring the arrival time differences of light along multiple paths. These studies produce H0 values around 73 kilometers per second per megaparsec, consistent with local Cepheid-based measurements. The lensing analyses are sensitive to both the expansion rate and the matter distribution along the line of sight. Theoretical developments in modified gravity also intersect with dark energy research. Theories such as FR gravity, Horndeski models, and massive gravity propose alterations to Einstein's equations that mimic or replace the effects attributed to dark energy. Surveys, including DES, KIDS, and HSC, have tested these theories by measuring the growth of structure, lensing shear correlations, and cluster abundances. Constraints are tightening. Deviations from general relativity are now limited to roughly 10% or less on scales of 1/100 megaparsecs. These limits, combined with supernovae and BAO data, suggest that if dark energy is responsible for the H0 tension, its behavior must be nearly identical to a cosmological constant on large scales, while subtly influencing local expansion rates. Experimental attempts to detect dynamic dark energy signatures are underway. The Dark Energy Spectroscopic Instrument, operational since 2020, is mapping over 35 million galaxies and quasars to Z is approximately equal to 3. DZ's high-resolution spectra allow measurement of BAO, redshift space distortions, and the growth of structure with unprecedented precision. Similarly, the Euclid mission, launched in 2023 by ESA, combines weak lensing and spectroscopic galaxy surveys over 15,000 square degrees to probe dark energy evolution directly. These campaigns aim to test whether the equation of state of dark energy deviates from 1 at the sub% level, a key threshold for reconciling local and large-scale H0 values. Type Ia supernova standardization depends on the assumption of a constant dark energy background. Recent studies, led by David Rubin and Gabriel Brute, have explored systematic uncertainties in supernova luminosities, including host galaxy mass, metallicity, and local star formation rate. These effects slightly adjust H0 estimates, but do not fully account for the roughly 6 kilometers per second per megaparsec difference between local and early universe values. Even subtle anisotropies in expansion can influence local H0 measurements. Observations of the kinetic Sunyaev-Zeldovich effect in clusters by SPT and ACT provide limits on bulk flows across hundreds of megaparsecs. Velocities exceeding a few hundred kilometers per second would imply inhomogeneous expansion that could bias local H0 determinations. Current constraints show flows smaller than 250 kilometers per second on scales of 200 megaparsecs. Cross-correlations between multiple datasets, including DESY-like BAO measurements, lensing data, supernova catalogs, and CMB-derived parameters, allow simultaneous fitting of H0, W, and matter density omega m. Analyses by Planck, DES, and BOSS indicate that small deviations in W on the order of 0.02, 0.05 over redshift 02 are not ruled out. Observations across supernovae, weak lensing, clustering, clusters, and gravitational lenses provide data on dark energy's role in cosmic acceleration. Theories and models consider whether dark energy varies with time, responds to local matter density, or interacts with gravity in ways not yet captured by the standard model. New measurements continue to refine constraints on its properties and influence on cosmic expansion. Modified gravity and broken assumptions. As cosmologists have sharpened their measurements of the universe, the possibility that general relativity might not tell the whole story on cosmic scales has gained attention. Einstein's equations have passed every test in the solar system, and even in strong gravity regimes, such as neutron stars and black holes. Yet, the persistent Hubble tension has prompted researchers to question whether the familiar laws of gravity remain unchanged across the vastness of intergalactic space. If gravity behaves differently over tens to hundreds of megaparsecs, the apparent acceleration of the universe and the inferred expansion rates could be misinterpreted. The most widely explored modifications fall into a class of theories known as F-R gravity, where the Einstein-Hilbert action is generalized by replacing the Ricci scalar r with a more complex function F-R. Researchers such as Antonio de Felice and Shinji Tsujikawa have shown that these theories can mimic dark energy, producing accelerated expansion without invoking a cosmological constant. Observationally, FR models can influence both the growth rate of cosmic structure and the lensing of light from distant galaxies. Galaxy surveys such as BOSS and eBOSS have placed constraints on these deviations, limiting the strength of modified gravity effects to less than 10% on scales of 10^200 megaparsecs. Horndeski theories extend this idea by introducing scalar fields that interact with gravity in non-trivial ways. The work of Claudia de Ram, Filippo Venizzi, and Lavinia Heisenberg has explored how these scalar-tensor interactions can alter the expansion history, particularly at late times. By adjusting the coupling strength of the scalar field to matter, models can produce Hubble constants compatible with observations and large-scale structure. Observational limits from the speed of gravitational waves, measured to match the speed of light, to within 1 part in 10^15 by LIGO and Virgo, following the neutron star merger GW170817, constrain Horndeski models that would predict deviations. Massive gravity, first formulated by Claudia de Ram and Gregory Gabadadze, represents another bold departure. In these models, the graviton, the hypothetical quantum carrier of gravity, possesses a tiny mass, altering the force law over cosmological distances. A non-zero graviton mass can reduce the effective gravitational pull on the largest scales, mimicking the effects of dark energy while allowing local expansion to appear faster. Observational constraints from galaxy clustering, cluster dynamics, and lensing currently limit the graviton mass to less than 10^-30 electron volts, but even this minuscule value could produce measurable effects over gigaparsec scales. Testing modified gravity requires both precision and scale. Weak gravitational lensing surveys provide a key probe, measuring how light from distant galaxies is deflected by intervening matter. The Canada-France-Hawaii Telescope Lensing Survey and the Hyper-SuPrimeCam survey have mapped shear correlations across millions of galaxies, providing sensitive tests of the growth of structure. Any departure from general relativity would alter the rate at which clusters form and the amplitude of lensing signals. Current results constrain deviations from general relativity to roughly 5–10%. Galaxy clustering provides a complementary avenue. The Baryon Oscillation Spectroscopic Survey, which measured redshifts for over 1.2 million galaxies, and the extended BOSS survey, which expanded coverage to 1.5 million galaxies, allow the reconstruction of the matter-power spectrum. Modified gravity alters the clustering amplitude and the scale dependence of baryon acoustic oscillations. Analyses led by Florian Beutler, Will Percival, and Shadab Alam indicate that standard WCDM provides an excellent fit to observed clustering. Another line of inquiry involves screening mechanisms designed to hide modifications of gravity in dense environments while allowing deviations in low-density regions. Chameleon fields, Weinstein mechanisms, and symmetron models exploit this idea. Researchers including Justin Curie, Lam Hui, and Philip Brax have studied the effects of these mechanisms. Observations of dwarf galaxies in low-density environments, particularly using the MUSE instrument on the Very Large Telescope, have sought anomalous rotation curves or lensing signatures consistent with these mechanisms. Results suggest that any effect must be smaller than 5% in these environments. Cluster dynamics offer another window. The Planck satellite's catalogue of over 1,200 galaxy clusters, combined with X-ray observations from Chandra and XMM Newton, provides detailed mass profiles and estimates of the gravitational potential. Modified gravity would influence the ratio of lensing mass to dynamical mass in clusters. Analyses by Mauro Serino and Stefano Ettori indicate that departures from general relativity are small. Simulations of structure formation in modified gravity scenarios have become increasingly sophisticated. Projects such as the Elephant simulations, led by Baoju Li and collaborators, and the ISIS simulations, designed by Marco Baldi and David F. Mota, model millions of galaxies under alternative gravity laws. These simulations show that even subtle modifications can alter halo formation rates, void statistics, and peculiar velocities, all of which influence local measurements of expansion. Importantly, some simulations suggest that peculiar velocities could be slightly higher in modified gravity scenarios, potentially biasing local H0 measurements upward by a few kilometers per second per megaparsec. Pulsar timing arrays provide independent tests of gravity over large scales. Arrays such as Nanograv, the European Pulsar Timing Array, and the Parkes Pulsar Timing Array monitor millisecond pulsars to detect long wavelength gravitational waves and deviations from general relativity. While the primary goal is to detect the stochastic background, these arrays also constrain modifications to the inverse square law of gravity over kiloparsec to megaparsec scales. Current bounds are consistent with general relativity to within 1–2%, placing tight constraints on theories that could mimic dark energy and influence local H0 measurements. Cosmic voids, vast underdense regions, amplify the effects of modified gravity in ways that dense environments suppress. The Void Galaxy Survey and studies using the Sloan Digital Sky Survey have examined hundreds of voids, ranging from 10 to 50 megaparsecs in radius. Simulations predict that in F, R, or chameleon models, the expansion rate inside voids could be faster than in surrounding regions, effectively producing a higher local H0. Observational evidence shows slight enhancements in galaxy velocities within voids. But the signal is subtle, typically a few tens of kilometers per second, leaving open the possibility that void-enhanced expansion plays a minor role. Local distance indicators, including Cepheids and masers, sample environments that may be slightly biased toward overdense or underdense regions. Researchers including Federico Marulli and Carlton Bohr are exploring correlations between galaxy environment and H0 determinations using deep spectroscopic and imaging surveys. Future observatories will enable detailed tests of modified gravity. The Vera C. Rubin Observatory's legacy survey of space and time will catalogue tens of billions of galaxies, mapping voids, filaments, and clusters. The Nancy Grace Roman Space Telescope will perform high-precision weak lensing and supernova surveys, probing deviations from general relativity on scales of 1/1000 megaparsecs. Combined with DESI and Euclid, these missions will provide measurements to constrain small departures from Einstein's equations. Observational tests of modified gravity now use multiple approaches, including lensing, clustering, voids, and pulsars. Data from these measurements provide constraints on deviations from general relativity, including effects on distance measurements, structure formation, and local expansion. Early dark energy and a faster infant universe. The idea that dark energy might have acted differently in the early universe has emerged as one of the most intriguing avenues for resolving the Hubble tension. While the cosmological constant is traditionally considered constant over cosmic time, several researchers have proposed that a transient form of dark energy could have briefly influenced the universe's expansion within the first few 100,000 years after the Big Bang. This early dark energy would leave a subtle imprint on the cosmic microwave background, while allowing the universe to appear to expand faster at later times, potentially reconciling the conflicting Hubble constant measurements. The initial theoretical framework for early dark energy was explored by Rachel Bean, Daniel Eisenstein, and others in the mid-2000s. These models posit a scalar field, similar in nature to the quintessence field, which contributes a small fraction, typically around 5% of the total energy density during the epoch of recombination, roughly 380,000 years after the Big Bang. Unlike the cosmological constant, which dominates the energy density only in the last few billion years, early dark energy would briefly accelerate expansion without significantly altering the formation of large-scale structure. Observational signatures of early dark energy are subtle yet detectable in precise measurements of the cosmic microwave background. The Planck satellite, which mapped temperature and polarization fluctuations with unprecedented resolution, provides critical constraints. By analyzing the angular size of the sound horizon and the amplitude of the acoustic peaks, cosmologists such as Eleonora Di Valentino, Steven Weinberg, and Licia Verde have constrained the contribution of early dark energy to less than 5% of the total energy density at recombination. This fraction can alter the inferred Hubble constant by approximately 13 kilometers per second per megaparsec. Early dark energy can influence the sound horizon scale, the standard ruler embedded in the primordial plasma. The sound horizon sets the distance that acoustic waves could travel before recombination and underpins the calibration of baryon acoustic oscillations and the CMB-derived Hubble constant. If early dark energy briefly increased expansion before recombination, it would reduce the sound horizon scale, affecting the inferred H0 value from CMB measurements. Researchers including Mark Kamionkowski and Wayne Hu have studied how a 2-3% reduction in the sound horizon could change H0 estimates. Supernova surveys and large-scale structure provide complementary tests. The Dark Energy Survey, which observed over 3,000 type Ia supernovae across redshifts 0.1 to 1.2, and the Kilo Degree Survey, mapping weak lensing and galaxy clustering, constrain the behavior of dark energy at later times. Early dark energy models must be consistent with these datasets, limiting the scalar field's persistence and requiring that it decay or become dynamically irrelevant by redshift 10, well before galaxy formation dominated the cosmic landscape Failure to satisfy these constraints would produce tension with the observed distribution of galaxies and the amplitude of matter clustering, quantified by sigma 8, the standard deviation of density fluctuations on 8 megaparsec scales. Particle physics has also entered the conversation. Certain early dark energy models invoke ultralight axion-like particles with masses around 10^-27 to 10^-28 electron volts. These fields oscillate rapidly and can contribute to the total energy density transiently. Researchers such as Lam Hui, David Marsh, and Javier Redondo have studied how these axions could affect the expansion rate while remaining consistent with nucleosynthesis and the observed abundances of helium and deuterium. Constraints from the Atacama Cosmology Telescope and the South Pole Telescope further restrict the contribution of any new relativistic species to the effective number of neutrino-like particles, NEF, ensuring that early dark energy scenarios remain compatible with precision cosmology. Simulations of cosmic evolution under early dark energy reveal consequences for structure formation. Using high-resolution N-body simulations, researchers including Fabio Fontenot and Matteo Viel have shown that early dark energy slightly suppresses the growth of massive clusters, altering halo mass functions by a few percent at redshifts greater than 1. CMB lensing provides another probe. The Planck collaboration's lensing maps, constructed from 4-point correlations in temperature and polarization, measure the projected mass distribution integrated over the line of sight. Early dark energy modifies the lensing amplitude because the additional expansion slightly delays structure growth. Analyses by Alessandro Melchiori and David Spergel indicate that lensing measurements are consistent with early dark energy fractions of up to 4%. Time delay cosmography using gravitationally lensed quasars provides an independent probe. The H0 Leichow collaboration, which monitors 6 lensed quasars with multiple time delay measurements, is sensitive to the expansion rate integrated along the light path. Early dark energy slightly changes the inferred distances to lensing galaxies and sources, altering derived H0 values by 1-2 km per second per megaparsec. Recent surveys targeting the epoch of reionization intersect with early dark energy constraints. Observations of the 21 centimeter line by the hydrogen epoch of reionization array and the LOFAR telescope trace the ionization history of the intergalactic medium from redshift 6 to 15. Researchers including Anastasia Fialkov and James Webb Space Telescope collaborators have begun to incorporate these high redshift observations into models of early universe expansion. The early dark energy hypothesis also intersects with cosmic neutrinos. If the early universe included an additional component of dark energy, it could alter the thermal history of relic neutrinos and their contribution to the radiation density. This shifts the ratio of baryons to photons and affects the damping tail of the CMB power spectrum. Analyses by Julian Lesgourg and Olga Mina show that current constraints from Planck allow for only a few percent modification. Laboratory experiments and theoretical modeling continue to refine the parameter space. Constraints on light scalar fields from fifth force searches and equivalence principle tests, such as those conducted by the Hewitt-Wash group at the University of Washington, indicate that any early dark energy candidate must decay or otherwise become effectively undetectable at late times. Future missions will provide additional observational constraints. The Nancy Grace Roman Space Telescope will provide deep infrared observations of type Ia supernovae at redshifts up to 2, while Euclid will map tens of millions of galaxies and perform high-precision, weak lensing surveys. Combined with next-generation CMB experiments like CMBS-4, these observatories will refine measurements relevant to early dark energy models. Early dark energy models involve scalar fields, ultralight particles, neutrinos, and the CMB power spectrum, creating multiple observational effects. Each observational probe contributes to constraining these models, including local expansion measurements, structure formation, and late-time observations, neutrinos, hidden particles, and extra physics. While early dark energy provides one avenue to explain the expansion tension, cosmologists have also turned their attention to particles that are either nearly invisible or completely unknown. Neutrinos, long considered nearly massless and weakly interacting, have proven more consequential than once believed. Experiments in the late 1990s, notably Super Kamiokande in Japan and SNO in Canada, confirmed neutrino oscillations, revealing that these particles possess mass, albeit minuscule. The discovery reshaped particle physics and left cosmologists wondering whether the properties of neutrinos might influence the expansion history of the universe. In standard cosmology, 3 active neutrino species contribute to the radiation density, influencing the rate at which the universe cooled and expanded in its earliest epochs. The effective number of neutrino-like species, Nef, is expected to be roughly 3.046, accounting for subtle interactions and thermal effects. However, if additional light species exist, sometimes called sterile neutrinos, they would increase Nef and subtly alter the sound horizon, similar to the effect of early dark energy. Recent Planck analyses constrain Nef to 2.99 plus or minus 0.17, leaving a small window for extra radiation-like particles. Sterile neutrinos are particularly intriguing because they do not interact via the weak force, making them invisible to most detectors. Laboratory experiments, including the LSND and Mini-Boon experiments at Fermilab, have hinted at anomalies consistent with one or more sterile neutrinos with masses around 1 electron volt. While these results remain controversial, theorists such as Kevork Abazagian and Sylvia Pascali have explored the cosmological consequences. A sterile neutrino present in the early universe could raise H0 inferred from the CMB by 1-2 km per second per megaparsec. The particle must also decay or decouple appropriately to avoid conflicting with Big Bang nucleosynthesis or galaxy formation. Beyond neutrinos, cosmologists have proposed other hidden particles and forms of dark radiation. Ultralight axion-like particles with masses between 10 (-33) and 10 (-27) electron volts could behave as a form of cold dark matter or dark radiation, depending on their interaction history. Fabio Capella and David Marsh have explored scenarios where these fields oscillate in the early universe, contributing transiently to the energy density without leaving a significant imprint on the large-scale structure. Constraints come from a variety of sources. The Lyman alpha forest traces intergalactic hydrogen absorption at redshifts 2, 5, while galaxy cluster counts from the South Pole Telescope provide limits on matter clustering. Both observations tightly constrain the fraction of energy density that hidden particles could occupy, generally limiting it to a few percent. Laboratory experiments complement cosmological observation. The Katrin experiment in Karlsruhe, Germany, measures the electron neutrino mass directly using tritium beta decay, aiming for sensitivity around 0.2 electron volts. If neutrinos are heavier than expected, or if additional species exist, the inferred expansion history of the early universe could be affected. Similarly, searches for weakly interacting massive particles or dark photons in underground laboratories, such as Xenont in Italy and Lux Zeppelin in the United States, test whether hidden sectors might carry additional energy density that subtly alters cosmic expansion. The influence of these particles on the Hubble constant operates through multiple mechanisms. Additional radiation increases the expansion rate before recombination, reducing the sound horizon imprinted on the cosmic microwave background. A smaller sound horizon then translates into a higher inferred H0 when interpreting the CMB using WCDM. Conversely, the presence of massive neutrinos suppresses the growth of structure at late times, affecting galaxy clustering, lensing, and supernova distances. Researchers, including Shirley Ho, Neil Dalal, and Raul Jimenez, have analyzed these effects using combined datasets. Some exotic proposals extend beyond neutrinos and axions to entirely new physics. Hidden sectors that interact only gravitationally, sometimes called dark sectors, could harbor particles that decay or transition between relativistic and non-relativistic states. Lisa Randall and Manoj Kaplinghat have proposed scenarios in which these sectors temporarily contribute to radiation energy density, boosting early expansion. Observational tests include precise measurements of baryon acoustic oscillations from surveys like EBOS and DESI, which measure the standard ruler across redshifts 0.33 with sub% accuracy. Any deviation caused by hidden particles would manifest as a mismatch between the predicted and observed clustering scales. Cosmic neutrinos themselves provide additional leverage. The cosmic neutrino background, analogous to the CMB, remains undetected directly but affects cosmological observables through its contribution to radiation density. The proposed Ptolemy experiment aims to detect relic neutrinos via capture on tritium, potentially providing the first direct measurement of this elusive background. Even without detection, precise modeling of neutrino decoupling and free streaming, led by theorists like George Fuller and Sylvia Pascali, constrains their mass and velocity distribution, which in turn influences the inferred expansion rate. Gravitational lensing offers yet another window into hidden physics. The deflection of light by galaxy clusters, quantified by weak lensing surveys like KIDS and HSC, measures the integrated matter distribution along the line of sight. Additional light species, or hidden sectors, modify the growth of structures, changing lensing amplitudes in measurable ways. Current analyses suggest that the addition of a single sterile neutrino species, or a small fraction of dark radiation, is still consistent with lensing data, though larger contributions are strongly disfavored. Supernova cosmology is also sensitive to extra physics. Type Ia supernovae serve as standard candles, but their inferred distances depend on the overall expansion history, which is altered by relativistic or semi-relativistic components in the early universe. SH0ES team members, including Adam Ries and Lucas McCree, have begun exploring the effects of early radiation density on the inferred H0. The interplay between particle physics and cosmology involves multiple constraints. Laboratory bounds, astrophysical surveys, and CMB measurements provide limits on viable models. Teams including Kevork Abazagian, Daniel Bollman, and Julien Lesgourg continue to explore the parameter space, running detailed Markov chain Monte Carlo analyses to test models against combined datasets from Planck, WMAP, SDSS, and DES. Even the properties of known neutrinos are still under scrutiny. Their mass hierarchy, whether normal or inverted, affects the growth of structures, with heavier mass sums suppressing clustering more strongly. Current cosmological constraints limit the sum of neutrino masses to less than 0.12 electron volts at 95% confidence, consistent with oscillation experiments, but leaving open the possibility of subtle effects on expansion. Future surveys, including CMBS4 and the Rubin Observatory's LSST, will improve constraints on both the sum of neutrino masses and the presence of additional relativistic species, further testing whether hidden particles contribute meaningfully to cosmic expansion. Particle physics and cosmology interact through small changes in early universe energy density, which affect the standard ruler, the growth of galaxies, and the inferred expansion rate. Ongoing experiments and refined datasets provide constraints on the contributions of neutrinos and hidden particles, cosmic variance, and the limits of our neighborhood. While hidden particles and exotic physics offer potential resolutions to the Hubble tension, astronomers have long considered a simpler explanation. Perhaps the discrepancy arises from the peculiarities of our local cosmic neighborhood. The concept of cosmic variance acknowledges that observations are limited by our position within the universe. Even if the cosmos is homogeneous on the largest scales, local fluctuations in matter density could produce apparent deviations in expansion rate. Understanding these effects requires a close examination of large-scale structures, voids, and overdensities surrounding the Milky Way. Observationally, the local group, the collection of galaxies bound by gravity, including the Milky Way and Andromeda, sits within a region sometimes called the local sheet. Extending roughly 7 megaparsecs in radius, the local sheet exhibits a velocity dispersion of around 40 kilometers per second, measured by high-precision Cepheids and tip-of-the-red giant branch stars. Beyond this, the Virgo supercluster dominates the local gravitational landscape. Galaxies within the Virgo cluster exhibit peculiar velocities up to 1,000 kilometers per second relative to the smooth Hubble flow, which must be carefully modeled to extract accurate expansion rates. Such local motions were historically a major source of uncertainty, but modern surveys have mapped these flows with unprecedented detail. Surrounding the local sheet is a vast underdense region known as the local void, first characterized in the 1980s and more recently quantified by R. Brent Tully and colleagues. The local void spans roughly 45 megaparsecs and contains significantly fewer galaxies than average. Its underdensity, estimated at 30–40% below the cosmic mean, creates a gravitationally induced outflow. Cosmologists have studied whether local underdensities, like the local void, affect measured H0 values through simulations and observational constraints. Quantifying the effect of cosmic variance requires precise mapping of galaxy distributions across tens to hundreds of megaparsecs. Large surveys, like the Sloan Digital Sky Survey, the 2-micron All-Sky Survey, and the Dark Energy Survey have catalogued millions of galaxies, providing a statistical framework for modeling local density fluctuations. Studies estimate that residing in a void as large and empty as the local void could increase the apparent local expansion rate by up to 1–2 kilometers per second per megaparsec. Simulations of cosmic structure provide further context. The Millennium simulation, led by Volker Springel and collaborators, traced the formation of dark matter halos and galaxies across a volume 500 megaparsecs on a side. By randomly sampling different regions, researchers measured the expected variance in local H0 values. The simulations predict that only extremely rare environments, representing less than 0.1% of cosmic volume, could produce deviations exceeding 3 kilometers per second per megaparsec. Subsequent work using the Bolshoi-Planck and Illustris TNG simulations, which include baryonic physics, confirmed these results. The probability that the local group resides in a void large enough to explain the full Hubble tension is exceedingly low. Despite these low probabilities, several teams have investigated alternative density configurations. For example, Keiichi Umetsu and colleagues examined lensing and galaxy cluster distributions within 200 megaparsecs to quantify local underdensities. They found modest variations in mass density consistent with the local void, but the gravitational effect on the Hubble constant remains insufficient to fully reconcile local and early universe values. Similarly, surveys of the velocity field in the nearby universe by Margaret Geller and John Huckra mapped flows around superclusters and voids, confirming that peculiar velocities diminish at distances beyond roughly 100, and 50 megaparsecs. Beyond this scale, the Hubble flow appears remarkably uniform, indicating that the local environment alone cannot account for the observed discrepancy. Cosmic variance also interacts with other observables. Baryon acoustic oscillation, BAO. Measurements from SDSS and EBOS provide a standard ruler across redshifts 0.13, effectively averaging over many large-scale structures. These measurements are consistent with the CMB inferred H0 rather than the local Cepheid-based value, implying that the universe as a whole conforms to the early universe expansion rate. If local underdensities were responsible, one would expect a gradient in H0 measurements with distance yet high-precision observations from supernova surveys, including the Pan-STARRS 1 Medium Deep Survey and the Carnegie Supernova Project, show no significant trend beyond 100 megaparsecs. Surveys of nearby galaxies reveal filamentary structures, walls, and minor voids within 5100 megaparsecs, such as the Great Attractor and the Sculptor Wall. These structures produce subtle anisotropies in galaxy velocities, contributing to the scatter in local expansion measurements. Projects like Cosmic Flows 3, led by Brent Tully, combine redshift-independent distances for over 17,000 galaxies to model these flows with high precision. The role of cosmic variance has also been investigated using Monte Carlo analyses. Researchers simulate tens of thousands of mock universes with randomly assigned density fluctuations matching observed power spectra. By placing virtual observers in each, they generate a distribution of local H0 values. Studies led by Licia Verde and Raúl Jiménez consistently find that even accounting for the full range of plausible underdensities, fewer than 1% of observers would measure H0 values as high as those observed locally. These results suggest that while local structure contributes to scatter, it cannot explain the systematic offset. Further insight comes from redshift-independent distance indicators beyond Cepheids and supernovae. Tip-of-the-red giant branch stars, surface brightness fluctuations, and water megamasers provide independent H0 measurements within and beyond the local sheet. Results from the Megamaser Cosmology project, which measures geometric distances to galaxies such as NGC 4258 and UGC 3789, yield H0 around 73 kilometers per second per megaparsec. Since these targets lie well outside the immediate local void, their agreement with Cepheid-based values reinforces the conclusion that local density variations alone are insufficient to explain the tension. Even considering the largest known voids, such as the KBC void, identified by Keenan, Barger, and Cowie, which spans roughly 300 megaparsecs with an underdensity of approximately 20%, simulations indicate a maximum H0 boost of 1.52 km per second per megaparsec. Observational campaigns using the Dark Energy Survey and the Hypersu PrimeCam have continued to map these voids and their surroundings, refining the mass and velocity profiles. Cosmic variance also imposes a practical limit on how precisely we can measure the expansion rate locally. Even with perfect instruments and unlimited observational time, the stochastic nature of galaxy positions, velocities, and mass distributions introduces irreducible uncertainty. Statistical treatments must account for this, combining datasets across multiple independent regions of the sky. Projects like SH0ES, Pantheon Plus, and Cosmic Flows adopt such approaches, explicitly modeling the impact of local density fluctuations and still consistently recover high H0 values. Investigations into cosmic variance show that local structures such as the local void, the Great Attractor, filamentary walls, and nearby clusters contribute measurable velocity perturbations. High local H0 measurements across independent indicators and distances beyond 100 megaparsecs remain higher than early universe values, suggesting that cosmic variance alone cannot fully account for the discrepancy. New telescopes, new tests, new pressure. As the limits of cosmic variance and local structure became increasingly clear, the focus shifted decisively to observation itself. The past decade has seen a substantial expansion in telescope capabilities, both on the ground and in space, allowing astronomers to probe the universe with higher precision than 20 years ago. These instruments were designed to test the Hubble tension across different scales, methods, and physical regimes. The James Webb Space Telescope, launched in December 2021, represents the most advanced infrared observatory ever deployed. Its 6.5-meter primary mirror, composed of 18 hexagonal segments, allows detection of Cepheids and tip-of-the-red giant branch stars at distances exceeding 40 megaparsecs. Observing in the infrared reduces uncertainties from interstellar dust, a long-standing source of systematic error in distance calibration. Early JWST observations of nearby galaxies, including NGC 4258 and NGC 5584, have already refined Cepheid period luminosity relations, confirming H0 values consistent with previous local measurements. The telescope's sensitivity has also allowed astronomers to measure faint supernovae in regions previously inaccessible, providing independent cross-checks on the distance ladder. On the ground, the Vera C. Rubin Observatory, set to begin full survey operations in 2026, will deliver the legacy survey of space and time, mapping billions of galaxies over half the sky. By detecting transient events, particularly type Ia supernovae, at unprecedented frequency, Rubin promises to reduce statistical uncertainty in local H0 measurements to below 1%. Its wide-field optical imager, with a 3.2 gigapixel camera, captures nightly sequences of galaxies spanning 9.6 square degrees per exposure, allowing for detailed light curves and accurate distance estimation. The combination of JWST's depth and Rubin's breadth offers a complementary approach. One probes faint and distant targets with exquisite resolution. The other captures a vast statistical sample to quantify rare events and environmental effects. In parallel, radio observatories have been revolutionizing geometric distance measurements. The next generation Very Large Array, planned for construction in New Mexico and Arizona, will enhance the Megamaser cosmology project by measuring orbital velocities in water megamaser systems to sub-kilometer per second precision. Already, instruments like the Green Bank Telescope and the Very Long Baseline Array have mapped dozens of megamasers, including NGC 4258, UGC 3789, and NGC 5765b, providing direct geometric distances with 2-3% accuracy. These measurements serve as an independent backbone for local H0 determinations, bypassing the astrophysical assumptions required for Cepheids or supernovae. High-resolution spectrographs are also contributing in novel ways. Instruments like the extremely large telescope's HIAS spectrograph, under construction in Chile, will provide velocity measurements of stellar populations and quasars with unprecedented precision. By measuring radial velocities to better than 1 kilometer per second in faint distant galaxies, HIAS will allow fine-grained mapping of peculiar motions and local flow corrections, further tightening the local expansion rate measurement. Similarly, the Subaru Prime Focus spectrograph, operating in Japan, will provide high-quality redshifts for millions of galaxies across 1,400 square degrees, enabling detailed studies of baryon acoustic oscillations and environmental effects on distance indicators. Space-based optical and ultraviolet observatories have also advanced the local H0 effort. The Hubble Space Telescope continues to play a critical role, with programs like SHOES+ and the Cosmic Assembly Near-Infrared Deep Extragalactic Legacy Survey extending Cepheid and supernova measurements to fainter and more distant targets. Observations of galaxies in clusters such as Coma and Fornax, as well as isolated field galaxies, provide independent cross-checks on distance calibrations and the effect of stellar population variations. JWST's infrared follow-ups have refined these calibrations further, reducing potential systematic offsets related to metallicity and crowding effects. The pressure to resolve the Hubble tension has also driven innovation in entirely different methods. Strong gravitational lensing time delays have emerged as a powerful independent approach. The H0-Likau collaboration, which analyzes multiple images of quasars lensed by foreground galaxies, now incorporates adaptive optics imaging from Keck Observatory, deep spectroscopy from Gemini North and South, and monitoring with the Las Cumbres Observatory network. By modeling the mass distribution of lensing galaxies and the propagation of light through intervening structures, these measurements produce H0 estimates around 73 km per second per megaparsec, consistent with the Cepheid and supernova distance ladder. The addition of the TD Cosmo program, which combines H0 Likau data with stellar kinematics, has further refined lensing-based constraints, reducing uncertainties to under 3%. Meanwhile, surveys of large-scale structure continue to provide indirect but complementary constraints. The Dark Energy Spectroscopic Instrument has mapped redshifts for over 35 million galaxies and quasars across the Northern Hemisphere, providing three-dimensional maps of matter distribution out to redshifts of 3. By measuring baryon acoustic oscillations in these datasets, DESI offers a distance scale anchored in the early universe, which can be compared with local measurements. Interestingly, these results remain consistent with Planck-derived H0 values, highlighting the tension with locally measured expansion rates and reinforcing the need for independent local probes. Time-domain astronomy has also entered the Hubble tension discussion in new ways. Projects like the Zwicky Transient Facility and Pan-STARRS capture thousands of supernovae per year, including early-stage explosions where intrinsic luminosities can be measured with higher confidence. Analysis of these events, especially when cross-matched with host galaxy properties and metallicity indicators, provides increasingly robust local expansion estimates. For example, a recent sample of 350 type Ia supernovae within 200 megaparsecs yielded a median H0 of 72.5 km per second per megaparsec, with uncertainties around 1.5%, reinforcing prior local results. Even gravitational wave astronomy has entered the arena. LIGO and Virgo's detection of binary neutron star mergers offers a novel standard siren approach. By combining the waveform-derived luminosity distance with host galaxy redshifts, these events provide H0 estimates independent of the traditional distance ladder. The 2017 detection of GW170817, along with its optical counterpart in NGC 4993, yielded a preliminary H0 of 70 km per second per megaparsec, consistent with Cepheid-based values, but with larger uncertainties. Future detections, anticipated at rates of dozens per year with upgraded facilities, promise to refine standard Siren H0 estimates to better than 2%. Local measurements, including Cepheids, supernovae, masers, and gravitational lenses, consistently return higher expansion rates, while large-scale structure, BAO, and early universe measurements remain systematically lower. The precision of JWST, Rubin, DESI, ING-VLA, and gravitational wave facilities increases statistical weight and reduces potential systematic uncertainties. The combination of depth, breadth, and methodological diversity allows cross-validation of distance indicators. JWST's infrared observations of Cepheids and supernovae in the same galaxies observed by HST provide tests of calibration consistency. Rubin's supernova light curves, when matched with DESI redshift maps, can identify environmental dependencies that might bias H0 estimates. Megamaser distances provide geometric anchors independent of stellar populations, while gravitational lensing time delays probe H0 in different physical contexts. The new generation of telescopes provides high-precision measurements of local expansion. The combination of improved instrumentation, massive surveys, and novel methodologies allows astronomers to measure expansion with sub-percent precision, test environmental dependencies, model peculiar velocities, and refine distance ladder calibrations. Despite these advances, local H0 values remain higher than early universe measurements, and ongoing observations continue to document this discrepancy. Simulations that don't match reality. As new telescopes delivered increasingly precise measurements, another frontier came under scrutiny: the theoretical simulations meant to reproduce the universe itself. For decades, cosmologists have relied on numerical models to test our understanding of structure formation, galaxy clustering, and cosmic expansion. The standard LCDM model, implemented in programs like Gadget 2, Illustris, and Eagle, has been remarkably successful at reproducing large-scale phenomena. The cosmic web, cluster mass functions, and baryon acoustic oscillations. Yet, as observational precision tightened, cracks began to appear, particularly when simulations were asked to replicate the very expansion rates measured locally versus those inferred from the early universe. The Millennium Simulation, launched in 2005 and run by the Max Planck Institute, was one of the first attempts to model cosmic structure, with billions of particles representing dark matter and baryonic matter across a cubic volume 500 megaparsecs on a side. The simulation accurately reproduced the statistical properties of galaxy clustering, halo mass functions, and void distributions. Yet when researchers attempted to extract Hubble-like flows from mock galaxy catalogues, discrepancies appeared. While the mean expansion rate over the entire volume matched the global H0 inferred from early universe measurements, local regions akin to the Milky Way could fluctuate by up to 4% due to peculiar velocities and density variations. These fluctuations were significant but insufficient to explain the nearly 10% difference seen in real observations, suggesting that simulations captured variance but not the full tension. More recent hydrodynamic simulations, including Illustris 2014 and its successor Illustris TNG 2018, incorporated gas physics, star formation, feedback from supernovae, and active galactic nuclei. These simulations traced billions of galaxies over cosmic time, producing realistic morphologies and mass distributions. Yet, even with the added complexity of baryonic physics, the expansion histories extracted from simulated galaxy catalogues are consistently aligned with early universe H0 values. When mock observers were placed within simulated Milky Way-like halos and measured local flows using synthetic Cepheids and Type Ia supernovae analogues, the derived H0 rarely exceeded early universe predictions by more than a few percent. The magnitude of the observed local early discrepancy was absent, highlighting a fundamental mismatch between model expectations and reality. The Eagle simulation, conducted by a European consortium, introduced yet another level of refinement. Spanning a cubic volume of 100 megaparsecs per side with over 10 billion particles, Eagle focused on the interplay between dark matter, gas cooling, and stellar feedback. Its detailed calibration allowed researchers to predict luminosities, colors, and chemical abundances of simulated galaxies, enabling more accurate mock distance indicators. When applying observational pipelines similar to those used by SH0ES, the resulting measured local H0 values consistently fell within 1–2% of the true simulated expansion rate, nowhere near the 9–10% discrepancy observed in the real universe. Even after accounting for environmental density, filamentary structures, and cluster proximity, simulations failed to reproduce the elevated local H0 reported by JWST, Rubin, and H0 Lickau datasets. Cosmologists also turned to extremely large volume simulations, such as the Horizon Run series and the Outer Rim simulation, which extended to gigaparsec scales. These projects modeled millions of dark matter halos, tracing filamentary networks, voids, and superclusters. The large volumes allowed statistically robust studies of cosmic variance and rare structures. Analyses confirmed that while local variations in expansion rates of a few percent were expected, the amplitude of real-world discrepancies exceeded those predicted for any plausible observer location. In other words, the observed high local H0 was unlikely to result from an unusually underdense or overdense patch of the universe alone, a finding that reinforced conclusions from Chapter 15 on cosmic variance. Attempts to reconcile the tension by adjusting feedback mechanisms and star formation efficiencies yielded mixed results. In Illustris TNG, increasing supernova and AGN feedback slightly reduced halo masses in dense environments, marginally increasing local H0 estimates. Yet these adjustments produced unrealistic stellar mass-halo mass ratios and over-suppressed star formation in intermediate mass galaxies, diverging from observed galaxy populations. Similarly, artificially enhancing baryonic winds in Eagle to mimic local underdensities produced modest increases in local expansion, but failed to achieve the nearly 10% discrepancy consistently across different mock observers. The simulations highlighted a stubborn conclusion. Standard astrophysical processes within WIL-CDM could not fully account for the tension. Simulations also revealed inconsistencies in the predicted distribution of peculiar velocities. In Millennium and Outer Rim mock catalogues, galaxies in cluster-like environments exhibited velocity dispersions up to 600 km per second, consistent with observations of the Virgo and Coma clusters. Yet the large-scale averaging of velocities reduced net local expansion deviations to a few percent. Observationally, the high local H0 inferred from Cepheids and supernovae persisted even when accounting for peculiar velocities up to several hundred kilometers per second. The discrepancy thus could not be dismissed as a result of unmodeled gravitational interactions or large-scale flows, further emphasizing the gap between theory and measurement. High-resolution zoom-in simulations targeting individual Milky Way analogues provided additional insight. Projects such as FIRE or feedback in realistic environments modeled galaxy formation in exquisite detail, resolving individual star clusters and supernova remnants. When mock observers applied standard candle techniques to these virtual galaxies, derived H0 values clustered tightly around the simulation's global expansion rate. Even with extreme variations in metallicity, dust attenuation, or star formation bursts, the local measurements rarely deviated more than 3%. These results reinforced a growing realization: local environmental factors, stellar population variations, and feedback processes alone were insufficient to replicate the real-world Hubble tension. Another layer of complexity emerged from simulations incorporating alternative cosmologies. Some groups explored early dark energy models or time-varying dark energy parameters within simulated universes, adjusting the expansion history prior to recombination. These simulations, often run using modified versions of Gadget or CMB-FAST, demonstrated that small injections of early dark energy could increase the inferred H0 in local-like regions. However, matching the precise amplitude of observed H0 discrepancies required fine-tuned parameters that risked violating constraints from CMB power spectra, nucleosynthesis, and galaxy clustering. The tension remained. Adjusting early, universe physics in simulations offered possible paths, but could not yet reconcile all observations naturally. Simulations also highlighted limitations in modeling observational pipelines themselves. Generating mock catalogues of Cepheids, supernovae, and masers requires assumptions about stellar evolution, population synthesis, and photometric calibration. Even small mismatches in period luminosity relations, dust corrections, or light curve fitting can introduce biases. Despite these complications, when teams ran end-to-end synthetic surveys on Millennium, Eagle, and illustrious TNG galaxies, the simulated local H0 systematically fell short of real measurements, suggesting that pipeline errors were unlikely to explain the discrepancy. The tension extended into computational cosmology's interface with gravitational lensing. Simulated lensing maps from the CosmoDC2 and TNG lensing projects, which combined dark matter distributions with baryonic galaxy models, reproduced observed time delays to within a few percent. However, when mock observers used these delays to infer H0, the resulting values aligned with the simulation's global expansion rate, not the elevated local measurements. Across decades of effort, billions of simulated particles, and increasingly sophisticated astrophysical modeling, no single approach reproduces the observed high local H0 while simultaneously matching early universe constraints. From hydrodynamic zoom-ins to gigaparsecond scale volumes, from baryonic feedback to alternative dark energy scenarios, simulations predict local variations far smaller than those observed. Mock supernova surveys in illustrious TNG galaxies, when compared with Zwicky transient facility and Pan-STARRS light curves, show that observed H0 values lie outside the predicted spread of simulated local H0. Megamaser measurements in NGC 4258 and UGC 3789 also fall outside simulated ranges. Time delay lensing H0 estimates in H0 Lycau galaxies exceed the values inferred from synthetic analogues in cosmological volumes. Gravitational wave standard sirens, when simulated in realistic galaxy catalogues, produce H0 distributions that do not reach the observed high local expansion rates. Current simulations, even at the forefront of computational cosmology, do not fully reproduce the high local expansion rates observed. They capture the large-scale structure, clustering, and statistical properties of galaxies with high fidelity, but systematically underpredict local H0 values. The precision of JWST, Rubin, DESI, and LIGO Virgo data provide stringent tests on these models, offering constraints on assumptions about dark energy, early universe physics, and gravity. A universe forcing a rewrite of its rules. By the time cosmologists examined the cumulative evidence from redshifts, distance ladders, supernovae, cosmic microwave background measurements, gravitational lensing, and simulations, a startling conclusion emerged. The universe was behaving in ways that defied the expectations set by decades of theoretical models. Every observational campaign, from Hubble Space Telescope Cepheid surveys to Planck CMB maps, pointed to a consistent internal logic, yet the different measures of cosmic expansion refused to converge. The tension between early universe and local measurements, crystallized in the Hubble constant, had been reinforced by increasingly sophisticated simulations that nonetheless failed to reproduce reality. Suddenly, the neat picture of a universe following a single, predictable expansion trajectory seemed incomplete. The observational contradictions were now impossible to dismiss as statistical flukes. The SH0ES Project's 2021 update, led by Adam Rees and his collaborators, reported a local Hubble constant of 73.2 km per second per megaparsec, with an uncertainty below 1%. In contrast, the 2018 Planck results placed H0 at 67.4 plus or minus 0.5 kilometers per second per megaparsec. This nearly 10% difference persisted across independent methods, including gravitational lensing time delays, maser-based distances in galaxies such as NGC 4258 and UGC 3789, and surface brightness fluctuations in elliptical galaxies. The consistency across these datasets made it increasingly unlikely that observational error or unaccounted for systematics alone could explain the discrepancy. Projects like Illustris TNG, Eagle, Millennium, Horizon Run, and Outer Rim consistently predicted local variations of H0 around 1–3%, far smaller than the observed nearly 10% gap. Adjustments to baryonic feedback, stellar winds, AGN activity, or early universe parameters produced only marginal shifts. Fine-tuning early dark energy models or introducing minor modifications to the neutrino sector created tensions with CMB power spectra and baryon acoustic oscillation measurements. Models that matched local H0 often violated constraints from structure formation, galaxy cluster abundance, or primordial element abundances. Galaxy clustering surveys such as BOSS, eBOSS, and DESI confirmed that baryon acoustic oscillation scales were in agreement with early universe H0. Cosmic voids, mapped in the Cosmic Flows 3 and 2 mass redshift survey, demonstrated underdensity patterns and peculiar velocities, yet they did not account for the elevated local expansion. Rare structures, such as supervoids spanning tens of megaparsecs, or massive superclusters, like the Shapley concentration, produced only minor local perturbations. Observational evidence did not indicate that our neighborhood in the universe was atypical enough to reconcile local and early universe measurements. Early dark energy models, explored by Mark Kamienkowski, Daniel Eisenstein, and others, proposed that a brief injection of additional energy could increase early expansion rates slightly, altering inferred H0 values while preserving the observed CMB patterns. Tuning such models to simultaneously satisfy supernova distances, BAO, and CMB anisotropies required narrow windows for timing, amplitude, and decay of the hypothetical energy component. Other possibilities emerged from particle physics. If neutrinos had non-standard properties such as extrasterile species, varying masses, or interactions beyond the weak force, they could influence early universe expansion. Experiments such as Katrin, Dune, and IceCube continue to probe neutrino mass hierarchies and mixing angles, while cosmological surveys constrain their impact on the CMB and large-scale structure. Similarly, hypothetical dark sector particles, including ultralight axions or self-interacting dark matter, could alter the expansion dynamics subtly. Yet the absence of direct detection in laboratory experiments or cosmological signatures beyond the Hubble tension imposed strict limits on these models. General relativity deviations on cosmic scales were explored through FR gravity, scalar tensor theories, and emergent gravity frameworks. Teams led by Baoju Li, Claudia de Rham, and Lam Hui simulated large-scale structure formation under modified gravity, finding small but measurable changes in galaxy clustering and halo growth rates. Some modifications increased the effective local expansion, but they often disrupted the match between WCDM predictions and weak lensing surveys, redshift space distortions, or cluster mass functions. CMB experiments beyond Planck, including the Atacama Cosmology Telescope and the South Pole Telescope, measured H0 independently, confirming Planck-inferred values. Polarization measurements, acoustic peak heights, and damping tail observations constrained the physical densities of baryons, dark matter, and radiation. Small changes to these parameters shifted the inferred H0 by fractions of a percent, not enough to explain the nearly 10% discrepancy observed locally. Cross-correlations with weak lensing maps and galaxy redshift surveys indicated consistent results across datasets. Gravitational wave standard sirens, first used with GW 170817, provided an independent probe of H0. The merger of a neutron star binary in NGC 4993 produced a direct luminosity distance, yielding an H0 estimate of 70 plus 12 meters per second per megaparsec. Future LIGO, Virgo, CAGRA, and Einstein telescope observations are expected to improve precision to levels comparable with Cepheids and supernovae. Initial measurements produced values near the high local H0. Adjusting dark energy parameters affects structure formation. Introducing new particles can influence Big Bang nucleosynthesis. Altering gravity changes weak lensing signals and galaxy rotation curves. Resolving the Hubble tension requires cross-disciplinary approaches. Researchers from institutions including the University of Cambridge, Harvard-Smithsonian Center for Astrophysics, Kyoto University, and the Max Planck Institute are investigating these effects. Computational cosmology remained central to testing new ideas. State-of-the-art simulations such as SIMBA, Illustris TNG 100, and the Vera Rubin Observatory's LSST mock catalogues allow researchers to implement early dark energy, modified gravity, or non-standard neutrino physics, and then generate synthetic observables for comparison with real surveys. Each iteration refined the plausible parameter space, but convergence remained limited. Simulations were unable to simultaneously reproduce all observational constraints, highlighting limitations in current models. JWST infrared photometry revealed Cepheids in galaxies beyond 40 megaparsecs, extending the distance ladder with high precision. DESI mapped tens of millions of galaxies over 14,000 square degrees, providing detailed views of large-scale structure. The Vera Rubin Observatory's LSST survey will deliver millions of supernova light curves over 10 years. Analyses of these datasets allow increasingly precise measurements of local and early universe H0 values. Measurements of H0 have implications for dark energy models, tests of general relativity on cosmic scales, neutrino properties, and assumptions in cosmic microwave background analyses. Differences between local and early universe H0 influence calculations of the universe's age, growth rates of large-scale structures, and evolution of galaxy populations over billions of years. Researchers are studying how these measurements interact with multiple cosmological parameters. High-precision measurements, simulations, and cosmological models consistently show differences between local and early universe H0 values. Analyses of distances, spectral lines, and simulated galaxies indicate that current LOCDM-based models cannot fully reproduce the observed local expansion rates. Observational evidence from JWST, DESI, LSST, and gravitational wave standard sirens, combined with simulation results, highlights areas where standard assumptions about dark energy, gravity, and early universe physics are being tested. Researchers continue to refine models and datasets to quantify these discrepancies.